And now?
Yeah, all is in order. Yeah.
So it's everything okay?
Yes.
Okay. So first, I would like to thank the organizers to give me the opportunity to talk about our research. It's an ongoing research, so we have some results, but it's not, we will certainly work further on the problems here. So I will talk about hybrid star construction using with our extended linear Sogno model. Here is some overview. Here I try to motivate our research, then motivate our model. We parameterize our model at vacuum, so T equals 0, mu equals 0. Then we extrapolate to finite temperature and finite chemical potential. And then we I will present some results about neutron stars. And I will have some summary and I have some backup. So this Polyakov loop I will not talk about. So we are going to study dense, strongly interacting matter. This is the phase diagram of nuclear, of strongly interacting matter. At mu equals 0, high temperature, theoretically the problem is quite well under control by lattice calculation. And also now there are tremendous data studying this regime from LHC and also from RIC. And RIC now makes a scan, beam energy scan program, try to localize the expected critical point. On the other hand, from the theory point of view, that it's not sure that there is a phase transition. There is a first order phase transition, or all in the all phase diagram we have only crossover, because at mu equals 0 we have a crossover. It's quite well proven. So it's an assumption that we have a critical point, and it's also assumed that here during this line we have a first order phase transition, but it's not settled yet. For example, groups like Hasuda and his company, they assume that we have another critical point here, and then at t equals 0, we still have only a crossover. Uh, we do not know yet, so we need to study this direction as well. Unfortunately, no good theory, and there is definitely no high energy, heavy ion experiment here. There will be some experiments somewhere here, Nika and Fair, but it will come in the future and it will not go very deep down. So let's study the dense matter at t equals 0. Uh, Now the question is there a phase transition? If yes, at which density? Or what is the properties of these phases? Because it's also not clear. At something 20, 30 years ago, it was assumed that the hadronic matter goes over to quark-gluon plasma, and this quark-gluon plasma is weakly interacting. Now we learned that at least at mu equals 0, very high temperature, the quark-gluon plasma is not weakly but strongly interacting matter. But at t equals 0, it can happen that other side of the hadronic matter, it's some color superconductivities. So we do not know yet. Let's look what we might know about this phase transition. So it's a very primitive calculation that the proton volume is more or less 2.5 cubic Fermi if we assume the electromagnetic radius we use the electromagnetic radius of the proton. We know that the densest packing with hard shears is 74%. So if we use these two numbers, we get that the maximal density where the protons still not overlap is 0.3 1 over Fermi cube, which is more or less 1.8 times rho 0. So below 1.8, there is no reason to have any phase transition. But of course, we know that in the proton, the outer layers are pion clouds and some mesonic clouds. So it is, even if we increase the density above with 1.8, there is no, it's not sure that we should have some kind of deconfinement or something like that. Now let's look the other extreme, right, right hardcore potential. Here the radius of the potential is more or less the half of the electromagnetic radius. So if I simply count that, then up to 15 times rho zero, the hardcore spheres still do not overlap. So theoretically, it's possible that even up to 15 times rho zero, we do not have a real, we need not have a real deconfinement transition. Although, of course, there are a lot, the pion clouds should overlap. So this is really an extreme number. But between 2 and between 15, there is no real good reason to know where is this phase transition. What we learned from heavy ion collision, that at least there is no sharp transition until 2 to 3 times rho zero. So from there, we also do not get much information. Of course, it can be that the phase transition has crossover, and then in a heavy ion collision, we will not detect it. So therefore, it's very interesting to study neutron stars where we have a very dense matter, and we can find observables which are sensitive of the phase of the matter inside the neutron star. So that means it's neutron, to understand neutron stars, it's a challenge because it exists in the universe. So if it exists, we would like to understand, but it's also a possibility to learn about strongly interacting matter. So neutron stars probably contain the densest matter in the universe. So at the same time, it's laboratory for strong interaction. It's a sketch for the neutron star structure. There is a core, there is a outer crust, inner crust, and the core. So even the crust is very difficult or very complicated. It has a complicated object. It can have gnocchis, spaghettis, lasagnas. So very interesting objects outside the crust, but there you should know the nuclear physics very precisely to really calculate what is the state of matter at these very, very low densities. Above rho zero, you should use some kind of nuclear matter model. And if you assume you have some exotic phenomena, like quark matter, although actually Kurkela said that it's not exotic because exotic would be if the whole neutron star consists of only neutron and only hadronic matter. So most probably, at least according to him, and also in our calculation, it comes out that to describe the existing neutron star data, we need a quark-gluon core inside in the center, but there is no good evidence, so it's still you cannot make strong conclusions. When the 2 times solar mass neutron star was discovered, for a short time it was a real a challenge, because if you assume that you can have lambda and sigma in the matter, and they behave very similarly like the nucleons, then very easily a lot of neutrons will change to lambda or sigma, and then the equation of state became too soft, and you cannot produce then 2 times solar mass neutrinos. There are several ways out of this problem now. One is, if you assume vector repulsion, then you can get stiff enough equation of state. And also quite not a few years old calculation of the Weise that the 3-body repulsion increased the self-energy of the lambda and sigma. So they are not, there are very few, there should be very few inside a neutron star. Yesterday, Horst Stöcker told us that Of course, three-body forces is you should not use three-body forces. Rather, you should use relativistic physics. Of course, he is right. But if you go to higher orders, two-loop calculation, then you already should find the effect is what Weiser call as three-body repulsion. But normally you never go up to two-loop calculation because it became too difficult. And this is the problem when you use some kind of perturbative methods, because here the coupling constants are large, so there is no reason why to skip higher order calculation. But anyway, it's a problem for all such kind of models. How to observe phases inside neutron star. One possibility which is well measured is the mass, radius, and the tidal deformability. The problem is that when you calculate these numbers, you integrate over the whole volume of the neutron star, and so they are integrated numbers, and it's very difficult with them differentiate between different structures. So even you can change the hadronic chaos such a way that you can get the same mass or radius or tidal deformability as with a neutron star with a quark core. There are two or three other possibilities which I will not discuss actually in the talk, but we will study in the future. At least we plan to study the air mode oscillation, since gravitational wave probe the whole volume, and you need a damping mechanism, and these depend on the viscosities, and these viscosities are very different, at least at the level of our knowledge now. So it can happen that we will get refined models where it will be more difficult to differentiate. But simply to look the figure on the left, you can have a normal hadronic matter, and there is a instability window above this purple line, and these are existing neutron stars. So these cannot live so long in this instability part. So probably this is not a good this hadronic matter calculation. So it's not, the viscosities probably are not correct. On the other hand, if they use interacting quark matter, then the instability is above these blue lines, and there are no neutron star above these blue lines. So it seems that at least this air mode oscillation calculation favors a quark matter inside the neutron star. Another interesting question, what we should understand the cooling of neutron stars via neutrino emission. Here is the problem of triangle inequality, and at the moment, probably both the quark matter and also the nuclear matter can solve the cooling via, for example, pairing, or I mean, the triangle inequality makes a problem, for example, for the Urca process, but you can go around it by if you assume some kind of pairing. But at the moment, it is also not settled yet. Another way of understand what is happening inside the neutron star is the merger, and this is the calculation of Resol and his group, and also Mateusz Hanuschke. He was talking yesterday, and they calculated the post-merger gravitational wave emission, and this is when there is no phase transition, and this is when at once there is some phase transition, and these are two different scenarios for the phase transition. So it seems, at least from the gravitational wave emission in a post-merger, one can see whether you can create a phase transition in neutron star merger or not, if you have good post-merger measurement. Unfortunately, the neutron star merger 3 years ago was too far away to have any possibility to observe these post-merger gravitational waves. Now, if we have an equation of state, then probably here everybody knows how to go. One has to, this is the Tolman-Oppenheimer-Wolfkow equation, and what the input is the equation of state. So if you know the pressure as a function of energy density, then you can integrate from zero central density out where until the pressure goes to zero, and then you can get the mass and you can get the radius as well. And if you change the central density, you can get a line where neutron stars can exist with a given equation of state. So it means we need an equation of state. The crust is, at least from my point of view, is quite difficult because it's not nuclear matter. You need different structures. So actually in our calculation, we use for the outer crust the BPS, but Bain-Patik-Sutherland potential equation of state. For the inner crust, we use the Nagelev-Voderin. And for at the moment, we are not able to calculate from our model the nuclear matter equation of state. So we use the TNE2 and TNE3, actually mainly TNE2. For the quark matter, we derived a model, and I will talk just now about this model. And we make a crossover with P interpolation of the nuclear matter and the quark phase. These are the equations. Actually, this is the same what Hatsuda and his group, Bain and Hatsuda, is doing with but in their case, the quark matter is described with a non-Bujono-Lazinho model. So what is our model? We built an effective model which has the right global symmetries. We compare the thermomites of the model with lattice at zero chemical potential, and then we extrapolate it to high chemical potential. Now our future plan is to generalize our model, or we include also a model for the hadron side. So not taking TNE2 or TNE3, because then it will get some ad hoc concatenation. So we would like to make the phase transition inside one model. And how we would like to do that? Benich and his group in these two papers describe the possibility how you can introduce some kind of backfield, and with that you can actually make smoothly between so change from nuclear matter to quark matter. But at the moment we are not there, but it belongs to our plan to do that. So what is our model, this quark meson model? The meson sector, we include the scalar and pseudo-scalar fields, and also the vector and axial vector fields. Vector interaction is very important if we would like to understand the repulsion inside neutron star. The Lagrangian is a very typical Lagrangian. It's very, very similar to the non-Bujono-Lazinho. We have this fourth order potential for the meson fields, kinetic energy term. This is the vector meson kinetic energy. Some mass term for the vector mesons. This is the external field, and this is Moskova-Toft, Kobayashi-Moskova-Toft term. So we also introduced the quark fields, and we also have a Yukawa term between the quarks and the vector mesons. These are where the details of the model is written. Here are some explanation what are the covariant derivatives, what are the fields, and in this model, since it has a fourth order interaction term, and we can have a broken symmetry like in the nature. So we have a spontaneous symmetry breaking. So we have to change our fields, and we have to expand our fields around some classical value. Of course, it makes a lot of difficulties. We have to shift fields. We have to diagonalize the mass matrix. We have to have a wave function renormalization. But in the end, we can calculate masses, decay widths, and then using these experimental measurable quantities, we have.
Georgie,
Yes.
there are 5 minutes left, please.
Okay. Okay.
Thank you.
I will hurry now. So we simply determine our coupling constants, and then we have our model. We include also the vector meson quark interaction. If we have a finite chemical potential, we have a condensate also for the vector fields. We can calculate it, and it's wrong. We can calculate the condensates by minimizing the ground canonical potential, and then we have actually everything. We can calculate all the interesting quantities. For example, here we show how the condensate behaves. This is the normal condensate, and this is the strange quark condensate at t equals 0. Some masses. We can calculate pressure and all the thermodynamical quantities, and here I show how good is our results. We can describe the interaction measure and also the speed of sound at mu equals 0. The points are the lattice calculation. And this is also the entropy, constant entropy lines in the chemical potential temperature planes compared to the lattice data. The same structure. Actually, from that, you can also learn that there is no critical point until 400 MeV chemical potential. Now, if we use this model, we can calculate we have then the equation of state, and then we can use solve the Tolman-Oppenheimer-Volkov equation. And this is our equation of state, where we change the density where the transition happens, the crossover happens. This is the 2 times, this is the 4 times. This belongs to 250 compressibility in the hardening side, and this is 300. You see that the compressibility has very small effect on the equation of state. On the other hand, if you look, this is the MR curve, the compressibility has a quite large effect. And also the density where you have a phase transition also has a very large effect. So these ad hoc parameters are really very important to understand. I can also study the GV dependent. GV is the coupling constant of the vector field. This is also, the effect is also quite large. So we should have some control on these parameters. And I also study the crossover widths. Crossover widths on this. So the width of the crossover has not large effect, but still we see that the compressibility has a very large effect. So this is up to know what we can talk, what we can say about our models, that the ad hoc parameters has quite large effect on the MR curve. So we should get something more precise. At least we would like to have some nuclear matter equation of state and inside a built-in phase transition and not some artificially done. We also calculated the tidal deformability. It's inside the window, so it's all the equation of state what we use are allowed via the result of the what we learned from the merger event. So some summary and conclusion. So our model can reproduce lattice calculation at chemical potential 0. And at the moment, our model, we can fulfill the present astronomical constraint, but we have a strong model dependent parameter. So the results depend strongly on the ad hoc parameters. So our plan is that we try to build in a model which handles equally hadronic and the quark phase. And we would like to then understand neutron star cooling and damping of the air mode oscillation. But these are at the moment quite far in the future, at least the last 2 points. Thanks for your attention. Thanks for
Thank you. Thank you very much. Very well on time. So, do we have any questions in the chat?
As of the moment, Luis, no, no one has asked a question yet.
Right. Okay. So we remind the attendees to write your questions in the Q&A chat. And if you have further questions, if you have questions later, you can contact the speakers. They will be available. I think a question just showed up, Steven.
I don't see it. If you see one, go ahead and read it.
Yeah, from Gabriela Grunfeld. Could you please show results with Polyakov loop?
So, of course, at mu=0 at high temperature, the Polyakov loop plays an important role. And I mean, this is the definition of the Polyakov loop. And we use it in the same way as all other people are doing that. The effect of the Polyakov loop is actually a modification of the Fermi-Dirac distribution for the fermions. You can call it as a statistical confinement, because if the Polyakov loop is 0, then the distribution function, here you have a factor 3. So it means it seems that 3 fermions occupy one position, and if the Polyakov loop goes to 1, then here you don't have this 3. Then the fermions occupy the Fermi sphere normally. So it seems that it has, at least statistically, mimics the confinement. But these 5 fields are condensates, and we obtain these 5 fields if we minimize the ground canonical potential. And these equations simply we can obtain if we we can derive it by this definition and going to a given gauge. It's a lengthy derivation, but you can do that.
Excellent. And, thank you.
I mean, if somebody interested, this is how the potential looks like for the Polyakov loop. It also shows that at t=0, we have a symmetric situation. At a non-zero temperature, we have a Z3 symmetry. So the symmetry is actually broken spontaneously.
Good, thank you. So there are no more questions. So we are going to thank Georgi for his nice talk. Thank you very much. So we are going to continue with our program. Deborah, can you please show your screen, share your screen, and please go ahead with your presentation.
Okay, thank you very much for Luis for hosting this session, and I'd like also to thank the organizers for the invitation and the opportunity to show my work, and for the huge effort to be hosting this online conference. So welcome to my home, and I'm going to talk about gravitational wave signatures, and afterwards I'm going to talk about magnetars. So this picture shows House and Taylor very happy when they learned they had been awarded the Nobel Prize in 1993. And the prize came because after the first binary pulsar was detected in Arecibo with this very precise pulse period, it was seen that there was a loss of energy, and House and Taylor identified this loss of energy as the first gravitational wave that was indirectly detected. Until 2015, when the LIGO and Virgo collaboration detected the first, directly the first gravitational wave, this GW 150914, that was the result of two colliding black holes. And then finally in 2017, GW 170817 was detected as the result of the merging of two neutron stars. And that's where my history starts. So this very nice slide was given to me by Francesca Gominelli, and I like it very much because it shows this, these two neutron stars coming to a final point, to the merging. And then you can see that the tidal field of the companion induces this mass quadrupole moment, which accelerates this coalescence. And the time of the coalescence is determined by the tidal polarizability that was just shown in the previous talk by Wolf. And he has also shown this expression, this tidal polarizability that depends on K2, which is the second order law of number, C, which is the compactness of the star, radius and mass of the star. So to obtain this tidal polarizability, we need an equation of state. And there are many equations of states in the literature. So for the first part of my talk, I'm going just to concentrate on relativistic mean field models. And I'm going to say that not too long ago, 6 years ago, we have tested 263 of the available models in the literature, and they were confronted with nuclear bulk properties. And only 35 of them were completely approved. We have to look at this result with care. It does not mean that the other equation of states are rubbish, but it just means that they did not satisfy the nuclear bulk properties we had chosen that were the most reliable at that time. Okay, from these 35 approved models, we selected 34 of them and we confronted them with astrophysical constraints. And only 15 were shown to be able to sustain massive neutron stars, even without hybrids. And then again, we tested these 35 models and with respect, okay, I'm listening to you. Cesar, is it okay?
Sorry.
Okay. No, I thought okay. So then we tested these 35 models and we confronted them with these gravitational waves, the GW, with the constraints coming from this gravitational wave. And then 24 of them were shown to lie inside this tidal polarizability confidence lines. But if we look at the results, only 5 of them can at the same time describe massive neutron stars and also satisfy gravitational wave constraints. So here are the results. So if we look at the left picture on the top, you can see that just, you don't have to be able, you probably won't be able to read all these labels, but you can certainly see that just a few of these curves cross this blue line, and where these two blue and orange line, which were obtained from Antoniadis and De Morestis results. So they show these massive stars. And then if we look at the picture in the bottom, you can see this tidal polarizability confidence lines, and you see that then these 24, almost all the models we have checked lie inside these confidence lines. But now it seems that there is still possible that even more massive neutron stars exist. And if this is the case, then even fewer equation of states can really satisfy these even more massive neutron stars. And I'm not even mentioning the hyperon puzzle that shows that when hyperons are included in the equation of states, then the equation of state becomes softer and the maximum mass decreases. Okay, so I'm going to show these pictures again. Also, the structure of this neutron star was already shown during this conference many times. This is also by Danny Page, who is responsible for this nice picture. And also Wolf has shown a similar picture in his last seminar. And then you can see that we have this crust, and this is a very important quantity because the size of the crust is reflected in the radius of the neutron star. And the crust has two parts. It contains an outer crust that also Wolf told us that he normally uses this BPS, equation of states. There are different prescriptions for this outer crust. And then there's the inner crust. And in the inner crust, we believe that this pasta phase structure exists. This lasagna, gnocchi, spaghetti, whatever. And then we go to the core of the neutron star. So now I'm going to talk a little bit about this pasta phase structure and which are the effects that they play when we calculate the second order law of number and tidal polarizability. So if you look at this, the first picture top, then there are a series of models. I've used also relativistic models. Those are quark model, quark-meson coupling models. You don't have to care too much about it, but what I would like you to see is that while all of these chosen models are very similar when we confront the outer crust, even with different prescriptions, and the core, when you look at this inner crust, then they can change a lot. And that's exactly where the pasta phase lies. So if we look at the influence of the pasta phase on the second order law of number, you can just look at the two black lines. That's a model with and without pasta, and also the two red lines. Then we also see a model with and without the pasta phase. Then the difference is smaller when we introduce this omega Rho interaction on the model. So it seems there is an effect on the second order law of number, but when we look at the tidal polarizabilities, you can see the red lines almost coincide and the black lines are not too far away from each other. So the effect seems to be really minor. And then at least when we compute these tidal polarizability effects, whichever we choose for the outer and the inner crust seems to be okay as far as there is some physics included in it. But the pasta phase can really be important for other things. When we use transport equations to obtain shear and bulk viscosity, for example, if we look at the magnetic evolution of neutron stars, then we need to compute electrical and thermal conductivities. And even when we observe these short gamma ray bursts, and if we calculate quasi-periodic oscillations, then the pasta phase can play an important role. And in our previous approximation, so I've calculated pasta phase with very different models, but in all of them, we had one geometry appear at each time. We did not have more than one geometry at the same density because our approximation was poor. But we have seen that these fluctuations have been confirmed in numerical simulations done with this MDS model, molecular dynamics simulation, which is computationally very expensive. So I have here one example, but there are many recent simulations with MDS, and they all take a very long time. So we have a prescription to compute these different geometries appearing at the same time, which relies on rewriting this thermodynamical potential related to the cluster, to the denser phase of the pasta, which depends on this number of particles, which I call A, which is protons and neutrons, because the density is very low. And then we have this free energy density and the related chemical potential. We obtain this probability distribution for each geometry, and then we can sum on all different geometries to compute the final probability distributions. So this has been recently published. And if you look at the pictures, you can see, if you look first at this low density, this on the left, you can see results for 1 and 5 MeV. And then you can see that let's look for instance only to the solid lines that were obtained for 1 MeV. We can see that although this 3D geometry is the most important one, we can also obtain a 2D geometry coexisting 2D geometry. And if we increase the temperature, then this becomes even more important because the 3D geometry decreases and the 2D geometry increases. Then if we move densities, then we see that now we have 1D and 2D geometries coexisting. And so we can compute in a very quickly way these coexisting phases with different geometries in the path of X. And then we haven't used this to compute bulk viscosities, for instance, but I'm sure this is going to be very nice because this is fast to do it numerically. So let's go back to neutron stars themselves. And then very recently, this was already shown here. And we've recently, in June, have seen that this GW14-08-918 was confirmed. And it was the result of a merging of a 23 solar mass object, which is clearly a black hole, and a 2.6 solar mass object, which is, can be the least massive black hole ever detected or the most massive neutron star ever detected. So far, there is this mass gap that goes from 2.5 to 5, where no compactable object has ever been detected. And so it seems there is something now inside of this mass gap. But if this object is a 2.6 neutron star, then maybe we are in even more trouble to obtain this massive object from good equation of states that satisfy nuclear matter bulk properties correctly. So then we would have to review this equation of states, but I would say that they are almost at the state of the art, or perhaps we can substitute these TOV equations that were also shown in the last presentation by Wolf by something that includes modified gravity. So if you look at this equation, for instance, you can see that there is this, I've used again another relativistic equation of state, this IUFSU, and you can see that it's very easy with this. This is a raster rainbow. So we have one modified parameter, one free parameter that comes from raster modified gravity prescription, and another one that comes from rainbow. We've joined both of them. So with just two free parameters, we can accommodate massive neutron stars and also low radii. So you can see, for instance, because if you look at this canonical star, we can see that this equation of states does something like this. So it really shifts towards the left so that the radius of a canonical star can be within the limits of what has been recently expected and we find in the literature. And not mentioning the hyperons, they can be also easily accommodated if we just substitute these TOV equations by this modified gravity, and this has just also been recently published. So now let's go to magnetars. Okay, let's see how much time I have. So we know NICER, which is this neutron star interior composition explored, was launched recently, and we already have the first observational results. And in 2030, this advanced telescope for high energy astrophysics, Athena, is expected to be launched. And then we are probably going to have much more constraints to go back and analyze this equation of states at the same time that we have more results coming from gravitational waves. So what do we know about magnetars? We know that the main neutron star manifestations, the mass is known to lie in between 1.44 and 2 something solar masses. The radius is of the order of 10 kilometers. It's very massive. And they are normally manifest themselves as pulsars powered by rotational energy or by accreting X-ray binaries. Okay, but magnetars do not fit into these categories. I see somebody with raising hand. I'm not sure if I should. Maybe I just go to the end and then I come back to see what's coming out.
Deborah, questions are only at the end through the Q&A. No, there's no question answering now. It's later during the Q&A.
Okay, thank you. So, so I'm talking about magnetars. So they don't fit into normal categories, but there are as many of them being detected. There are two classes of magnetars. So far, there is this catalog. If you go there, you see that not many of them have been confirmed. There are also some candidates, but they are either soft gamma ray repeaters, which are transient sources, or they are anomalous X-ray pulsars. And what are these guys? So here we have some pictures. One comes from the Crab Nebula pulsar, and it has a surface magnetic field of the order of 10 to the 12 Gauss, and the other one is just my imagination, and with a magnetic field 3 orders of magnitude higher, which is 10 to the 15 Gauss of this order. But we know that if we want to compute equation of states and if we include magnetic fields, these equation of states are only sensitive to magnetic fields larger than 10 to the 17 Gauss. So this is a problem depending on the calculations that we want to perform. But if we look at the crust core transitions, we can really see when the magnetic fields enter. And this is a very important point, because this crust core transition delimits the size of the crust, which influences the radius. So we can compute this phase transition by looking at spinodal stabilities and looking at thermodynamic in two ways. First, thermodynamically, which is obtained from the determinant of a matrix which is symmetric and which is written in terms of the second derivative of the free energy with respect to the constituents of matter, in this case, protons and neutrons. And I'm not going to enter into details. I'm just going to show you the results. And we can also compute this phase transition when we compute this spinodal region from the Vlasov equation. And then if you look at this expression, F is the distribution function and H is the Hamiltonian of the system. So those are the results obtained with different values of the magnetic field. They are always written, the labels are really small, probably even smaller for you, but you can see that this is, I will say what they are. They are always defined in terms of this 10 to the 13 Gauss. So first, top picture left, you see the density of protons in terms of the density of neutrons, and this round thing delimits the spinodal region. That's where matter is stable. If we draw the equation of states in beta equilibrium crossing this spinodal region, when it crosses, the point that it crosses gives us the transition density. So if you look at the first picture, you see 0 and 10 to the 14 Gauss, no difference as expected. We don't see anything there. But when we move to 10 to the 15 Gauss, we already see these tiny kinks, which are related to the filling of the Landau levels that appear when we have a density-dependent formulas. Then when we move to 10 to the 15 Gauss down, we see very clearly these Landau levels. And then if we increase even further the magnetic fields, then we can see it again. These Landau levels become larger. Okay, so this is the crossing point that I've just mentioned. So the first two top panels are thermodynamical results, and the lower panels are dynamical results, but the idea is the same. We just want to look at the crossing points. So if we look at 0 or very low magnetic fields on the left, you see it just crosses 1. So the transition density is well defined. But when we look at the panels to the right side, we see that it can cross more than once. So, and this is also model dependent. So it means that the crossing point or the transition density is not very well defined. So let's see how we can take care of this. So we've done two different calculations. The first one is based, yes?
5 minutes left, please.
Okay.
Thank you.
So the first one is based on the solution of the TOV. And then how can we obtain the crust thickness? So we've used this recipe by Hansel and collaborators. So if we know the core. We use the TOV to obtain the mass and radius of the core. And then we have this prescription for the mass and of the crust and for the radius of the whole neutron star. So we know that the size of the crust is the radius of the neutron star minus the radius of the core. And those are the results. So if we have two crossing points, then of course we have two different crusts. And at the last column, I show you the uncertainty we obtain in the difference between these two crusts. So if we look at this zero magnetic field, of course, just crosses one, we just have one result. For 10 to the, we always multiply by 10 to the 13, so to 10 to the 15 Gauss, we also have one. And then when we increase the magnetic field, it crosses more than once, it crosses 2 times in this case, and we have the different values for these two crusts, which I call L1 and L2, and then we have this uncertainty. So if we look at the size of the crust, you see that both L1 and L2 are of the order of 1 kilometer, which is probably too low, because there is a reference that calculated this precisely, as precisely as it could be done at that point, and the expected crust size was of the order of 2.4 kilometers for a 10, 11 kilometer neutron star. Then we computed again using this Lorine, which is a more sophisticated code that solves Einstein, Maxwell, and equilibrium solutions all self-consistently with this magnetic field equation of state. And then we re-obtain the same results. You just have to concentrate on L1 and L2, and then you'll see the rest of the results are the same. So this, we also have this uncertainty on the size of the crust. But if we look at L1 and L2, you see that this is maybe too big if we expect this crust size to be 2.4. Here we obtain around 3. And in fact, if the magnetic field is too high, which is 10 to the 17, which is the last line, then we have almost 4 kilometer crust size. So this is an important quantity that has to be seen again with other models to be better understood. So which are the uncertainties concerning magnetars or the magnetar equation of states? Can they be part of binary systems? If so, we can use this equation of states to compute this lambda 1 and lambda 2 confidence lines. How strong is the magnetic field inside of the stars? We really don't know, because we have observations that tell us that at the crust, the magnetic field is of the order of 10 to the 15 Gauss. And then, although these low magnetic fields do not affect the equation of state and the macroscopic properties we obtain, they do affect the crust-to-core transition. And then this has consequences if people want to calculate bleaches, for instance, and love numbers and tidal polarizabilities. The other thing we've noticed that the calculation with this Lorine code may be producing too big crusts based on this spinodal crust-core transition densities. And at the end, if we can include fluctuations and to the pasta phase with magnetic fields, then maybe we can help to describe better the inner crust of magnetars. So that's it. So the quest for the Holy Grail continues, wherever it comes from, equation of states, the Stov, Lorine, modified gravity. There are many different paths we can follow to improve the calculations. And I thank CNPq and INCT for supporting it. So I'll just interrupt this.
Thank you, Deborah, for this very nice talk. So it is question time. I think there are some questions already in the chat.
If you see some questions, Luis,
I must
be having difficulty because I don't have any of them on my list.
I can see the questions. I just need my glasses.
Okay, I'm going to read them.
Sorry, you have before read the questions, because some people, they don't have access to the questions. Okay.
Should I read?
You know, we'll have Luis can read those and you can answer.
Yes, I'm going to read them. Yeah. There is this question by Rafael Rias. Final parsec problem deals with the black hole binary components, helping them to get closer to eventually get merged and produce gravitational waves. Does this parsec problem also remain quite valid when you expect form a binary system consisting of 2 neutron stars?
I don't know. I cannot say anything about, I don't know anything about this parsec problem. And I don't know much about black holes. I normally work with neutron stars, so it requires a different gravity effect. So sorry, I cannot say anything about it.
Okay, no problem.
So I will probably not be able to answer the second question either.
Oh, right. Okay. So in any case, I'm going to read the third question now. Should we rule out equation of a state by RMF approach if a pulsar with mass higher than 2.3 or 2.5 solar masses is discovered? No evidence for alternative gravity is found. Also, no direct evidence for B field larger than 10 to 13 Gauss exists, right?
Hi, Henshin. No, we don't have to rule out equation of states by MRR because we can get some approaches, at least without hyperons, with massive, that satisfy massive stars, 2.3 or 2.5, but not many of them. You see, we've tested 263, and to obtain 2, we just got 35. So if we really want to have 2.5, and then there are some ways of including other meson fields as strange meson fields in between the hyperons that can also increase the maximum mass. So we can still tune a bit the equation of state within this mechanism to obtain a little bit higher equation of state. So it's not ruled out. So some things can still be worked out. That's true that there is no evidence for alternative gravity so far as I know, but maybe there are some things that cannot be normally described by general relativity, and many more people are relying on describing properties, relying on modified gravities to describe other properties. So I'm not going to mention them here because I'm not an expert, but I think that this is also something that can be better studied. And you were also right that there is no direct evidence, also as far as I know, for magnetic fields at least higher than 10 to the 15 Gauss at the surface of magnetars.
Thank you, Deborah.
I think now there is a comment.
A comment, yes, from Dorota Rosinska. Weisberg played important role in observation of energy loss from the pulsar.
Thank you, that's true.
For example, Weisberg, Taylor, Fowler, October 1981, gravitational waves from an orbiting pulsar. And the reference is Scientific American 245. I guess the volume, page 74. Yeah.
Yeah.
Would you like to say something?
I failed to mention that. That's right. That's perfect. Thank you.
Okay.
Nice comment.
Right. So yeah, those are the questions in the chat. So thank you very much for your nice talk, Deborah. So we now.
Thank you, Deborah. Thank you very much.
Thank you.
Luis,
Thank you.
Luis, may I show again the
Yes.
slide? One
Yes.
slide, okay?
Yes, yes, please go ahead, yeah.
Sorry. I lost my, no, it's okay. I found again. Okay, just to inform again, the modification for today, the last minute modification in the program, okay? So we have the last minute modification is Sri Piran talk moved to 11:30 a.m. and parallel session discussions moved to 12:30 p.m. Okay, thank you very much.
Yeah, Mexico City time, please. Take note.
Mexico City time. That's right. That's right.
Yeah, thank you, Cesar. So we are now ready for the next talk by Jörg. We can see you, Jörg. So
Yes.
please share your screen and you can go ahead with your talk.
Yes.
It is going to be 25 minutes. I'm going to tell you when 20.
Is okay, visible?
Yes, it is visible. Yes.
Okay. So good afternoon to Southern America. We are here in the evening, and thank you very much for the invitation to present the recent work at this conference. So I would like to talk today about the work which we did since a couple of years and made constantly progress, and that's the phase diagram and the transport coefficients from the Polyakov, Nambu, and Racine Lagrangian. And I would like to share with you why we do this work and how far we came up to now. Now, the recent results have been published in the FUSREF-C, which you see below, and all is done not only by me, but in collaboration with people from Frankfurt, that's Olga Soloveva and Elena Patkovskaya, and my postdoc and graduate students from Torres, Rinson, and David Fussot. Now, the question is what we, oh, now I cannot move, let me just, okay, I have to do it here. So the question which we ask and which you have asked already in several of the contributions which I saw, so Matthias Hanauske and David Plaschke were occupied with the same questions. So we are now able to do simulation of neutron stars and neutron star collisions just since a couple of years, and that's very impressive, as well as heavy ion collisions, which we did a little bit longer. But for all of these collisions, we need basically the same input, and that is basically the phase diagram of strongly interacting matter. So as long as we are close and not too far from thermal equilibrium, we need very concretely the entropy density, the pressure, or the energy density as a function of the temperature and the chemical potential. And if you look now in the two kinds of experiments which have been done, either by nature itself or in accelerators, we see that the simulations always requires about the same density. So in heavy ion collisions, we have densities between 0 and 4 times nuclear matter density. In the neutron star collisions, we have about 0 to 8 times normal nuclear matter density. But that is about the range we are interested in. And the big difference is, of course, that we have to deal once with symmetric matter in heavy ion collisions where U is equal D, so the number of up and down quarks is identical. Whereas in neutron star, we have a large enhancements of the D, we have to get better equilibrium. And for this reason, the equation of state looks a little bit different, but the basic ingredients from the strong interaction are the same. So it's very meaningful to advance in the same direction for the same questions. Now, why is this complicated to calculate? Why do we not just go ahead and calculate all these on our computers, which are now quite powerful? The problem is that we can calculate in the most powerful ways, that means on the lattice calculations, presently only the situation for which the chemical potential is disappearing. That means we have the same number of quark and antiquarks, and that is the situation which we have at the very high energy heavy ion collisions, but not at lower energy heavy ion collisions, neither at the neutron star business. So we have to do something in order to extend this knowledge from the lattice gauge calculation. Now, a little bit has been done by the people from the lattice gauge calculations themselves. They did a Taylor expansion or a similar expansion method. They take imaginary chemical potential, but all is basically expansion around the mu equals 0, chemical potential equals 0 line. And by this, we can expand if the mu over T, chemical potential over the temperature, is relatively small. But unfortunately, in neutron star as well as in heavy ion collisions, this is not the case. We have actually the situation that the chemical potential is larger than the temperature, and for this reason, expansion methods around the mu equals 0 do not work. Now, we can either in this way to assume something which is going on, or we can do and try to do not really a solution of QCD itself, because there we need the lattice, but for effective theories which are adapted to produce and reproduce a QCD in this sector where we are interested in. And today I would like to talk about one of these theories, which is exactly this. This is an effective Lagrangian, which is quite old already, and has been invented by Nambu and Jonas Lasinho quite a while ago in a completely different context. But this Lagrangian will allow us, and has allowed us already, to study the phase diagram of strongly interacting matter at finite chemical potential and finite temperature, so in the whole plane which we are interested in. Now, with this Lagrangian, we can make prediction for finite T in mu, and we need as an input, and that is also very important, not very sophisticated calculations, we need as an input only vacuum values, that means measured masses, which are absolutely undebatable, and in addition, the Young-Mills Polyakov loop calculations from the poor Young-Mills lattice calculations. Now, why we would like to use this Lagrangian? The reason is very simple. The Lagrangian shares the symmetries with the QCD Lagrangian. Also, there are local symmetries in the QCD Lagrangian and global symmetries in the NGL, but the symmetries are the same. And there is also a way to derive, not in a mathematical thing, but to explain which terms actually have been neglected if we come from the poor QCD Lagrangian to that which is described by the Lamborghini. Now, the Lagrangian Lamborghini have proposed, it's just written here. You see that the basics, the kinetic energy part, then we have a determinant which takes care about the UA1 symmetry breaking, the fact that the eta and the eta prime have not the same mass. The last term is the chemical potential. So the interesting term is the second term in the first line, which shows the psi bar psi squared and the psi bar gamma 5 lambda psi squared. So these are 4-point interaction. There means at one point, like in the Fermi theory of weak interaction, four particles which join the interaction vertex, and by this we have the advantage that we can calculate this. So the main approximation is in this approximation to have this type of interaction. Now the Lagrangian itself needs 5 parameters to be solved on a computer, and that parameters can be fixed by, as I said, vacuum values, the mass of the pions and the kaons, the eta and eta bar splitting, eta and bar splitting, which is basically determining the age, the pion decay constant, and the chiral condensate, all quantities which we basically get from experiment or just take from the tables. Now, if you look a little bit more in detail what has happened, I showed you we have this 4-particle interaction, and that means, in comparison to the normal interaction, what we have, when a particle and an antiparticle or two particles come together, they exchange a particle, in this case a gluon, but the gluon can be exchanged directly, it can be split another time in a quark-antiquark pair. So the propagation of the information on the quantum momentum from the one particle to the next particle is a relatively complicated thing. But now if the mass of this gluon which is exchanged is relatively large, or even larger than the exchange momentum, then we can contract this gluon, because we have a propagator q squared minus m squared, to something which is 1 over m squared, and by this we have basically eliminated the dynamics of the gluon. This is of course only possible if the mass of the gluon is relatively large as compared to the momentum transfer. But in the region where we are looking at, that means close and a little bit above the critical temperature, all effective calculations give you that the mass of the quarks is around 300 MeV, and the mass of the gluons in the same order. So we are really living in a situation where the momentum exchange is small as compared to the mass of the gluon. And that's allowed us finally to have a quark-antiquark or quark-quark interaction, such as a 4-point interaction. And by this, as I said, we can calculate the quantities we would like. The only problem is if we do this and if we adjust all things correctly, then we end up with the thermodynamical properties calculated by the partition form, as usually means the pressure, entropy density, and energy density, which does unfortunately for the situation at mu equals 0, where the lattice calculations are available, do not coincide with the lattice calculation, and therefore the value of predictions for finite chemical potential is not so clear, and one should work harder to get the agreement with the lattice scale calculation in this part where the lattice calculation exists. Now, the first way of improvement is to go to a Polyakov-Lamborghini model, which was invented by Wolfram Weise and collaborators. And by this, we have just now, in addition to the normal NGL Lagrangian, a coupling from with the gluon field, which is a large D in these equations in red one, and we have a gluon potential, which is a static potential, so the gluon is not a dynamical variable. And by this, we can now add this to our Lagrangian. We can calculate. We can also calculate the pressure. We can calculate the Polyakov loop, which appears then in this phi and in the potential. And even if we do this, the agreement is not very impressive with the lattice data. So quantitatively, we do not get agreement with this. Now, in order to show you what's happening, we have the normal NGL on the left-hand side, the PNGL on the right-hand side. These are the masses of the up, down, and strange from U equals 0 as a function of the temperature. You see the Polyakov loop makes the transition a little bit sharper, but in principle, the general tendency is about the same. Now, before I come to a little bit more sophisticated model, I would just like to say that we need, of course, if we have the phase diagrams, the quark part and the gluon part, and the Lagrangian has the quarks as a degree of freedom, the gluon as a mean field, but we have also the hadronic part. And for this reason, the question is how we can get in this whole game hadrons in the Lagrangian or from the Lagrangian. And this is possible because the 4-point interaction can be considered as a kernel for a beta-psi-beta equation. This is shown in the first graph here. So we have 4-point interactions, and we have a second 4-point interaction, and so on. So this is a geometrical series which we can sum up. And if we sum it up, we have exactly the propagator we have for a pion exchange or a kaon exchange, all depending on the big omega, which describes as a scalar, pseudo-vector particle. But the structure is exactly the same. So that you see in the left lower corner. And for this reason, we can identify this beta-phi-beta equation with the exchange of a meson and looking for the pole mass, for the pole of the T matrix of the exchange. We can determine the mass of the mesons in this calculation, and also these are depending on the temperature and the chemical potential. So the results you see here on the left-hand side for a couple of mesons as compared to the sum of the constituent quark masses which compose these mesons. And you see in the very low temperatures, the masses of the quarks are relatively high. They reach 800 or even 1000 MeV if one sums the two together, whereas the pion and the kaons are exactly at the level where they are because we have adjusted our parameters. And so it's really a big difference between the masses of both. The thermodynamical relevant quantities are then the low mass particles, that's the mesons which are in the system. And if you look a little bit on the left right-hand side, then you see it for one example, the pion, that how the constituent masses, the sum of the up and down mass go down, they meet at a certain given temperature the masses of the meson, and starting from then on, the quark, for higher temperatures, the quark are the essential degrees of freedom. The meson becomes mass becomes the width because the meson is not stable anymore. It integrates into the two quarks. Now, how to improve the agreement now with the lattice calculation? We have up to now calculated the Lagrangian and then the partition sum in the first order in NC, which is proportional to NC. And that means we include only the free particles and the Hartree interaction between the two particles. And now for doing better, we had two extensions which we performed in the last years. The one is going beyond Yen leading order in the number of colors. This includes directly the meson degrees of freedom, as I will show you, and the modification of the gluon potential to the presence of the quark, which is also something which is straightforward. Now let me start with the second one, the modification of the gluon potential to the presence of the quark. There is quite a history behind this because first of all, in the PNGL model, it has been calculated in the Young-Mills approach, that means with a critical temperature of 270 MeV. Later, it has been found out by Wambach and Pawlowski from Heidelberg and Darmstadt that the presence of a quark-antiquark pair in the gluon propagator reduces this effective temperature to 190 MeV. And what we did, we just assumed that asymptotically we have the right limit, but in between a temperature close to the phase transition temperature, we can have deviation. We took a form which is just given by here, which has the right asymptotic asymptotic limit, and determine the parameters in a way that we approach the equation of state of the lattice calculations for mu equals 0. Now this means that we have taken into account in an effective way that the quark and anti-quark pairs are not only present in the gluon propagator, but there are also degrees of freedom which are there, which can directly collide with the quarks, and by this reason we have another effective temperature than we have in these other cases. The second thing is technically a little bit more complicated to take the next order in the partition sum that you can do in taking into account all these diagrams which I show you in the top line. You can get to this paper and you find all the other ones which are necessary to complete it. In the end of the day, you have an additional second part, second sum of the partition function, which one can calculate. It is straightforward just by using the graphs. The impressive things and important things at the same time is if you do this, then you find that this contribution is nothing else than a mesonic contribution. So out of the quarks, and having defined the mesons as I did before, you can rephrase this additional part in the partition sum in terms of meson, which is shown in the last line. So that as the distribution function of the mesons plus a phase, and this phase can be calculated with the same loop which we had used already to calculate the mass of the mesons. So it's a straightforward way, and by this we can include now the next to leading order. Now the phases one can calculate directly. These are given here in the graphs which are on the top. The one is for the pion, the other is for the kaon. And if we have this modification added, then we can indeed reproduce the lattice data for mu equals 0, as you see in the lower plot. We have here the pressure, the entropy density, the energy density in the interaction measure divided by a t to a certain power from the lattice calculation. So the lattice calculation in the arrow bars are the shadowed area, and the calculation we have in this approach, which I just presented to you, are the lines which are in there. So besides in the interaction measure where we deviate a little bit at the temperature of 0.2 GeV, the rest is possible to recover the results of the lattice calculation. Now that's an important point, because now we have a solid ground which we need in order to develop as a non-Brunellesino to a finite chemical potential. We can attach our calculation to the lattice data at mu equals 0. We can do a little bit better. We can go make the Taylor expansion, the same Taylor expansion as lattice did, and recover by this the coefficient A kappa, which is always the same coefficient in all the type of applications. And you see the different lattice calculation with different methods in the graph, which is below. The upper values are from the different papers about this finite chemical potential expansion. And the green point, which is here on the bottom, is the calculations which we get. So even in the first order expansion of the equation of state towards finite chemical potential, we agree with the lattice data which are available. And that is not the only, we can also go to very large chemical potential, where again PQCD calculations are possible. That is done in this transparency on this graph here, where we compared our results with these calculations. So the calculations have a huge error bar. So for this reason, it's maybe not extremely complicated to be there, but on the other side, it's also not so easy. And our line, the blue line is our result. The yellow part is the PQCD calculation. So at very low chemical potential, at very high chemical potential, we can adjust to really PQCD or lattice calculations, and therefore we have confidence that we can now explore the part in between. Now, here some details of what's going on. We see here the pressure of the quarks and the gluons. You see the pressure of a negative, positive, the quarks is a positive pressure. The gluons partially a negative pressure because the potential gets attractive. The pions pressure here and the sigma pressure, this looks very smooth here for low chemical potential that we see in the NGL or PNGL already before, but it gets now for finite chemical potential now steeper and steeper, and I will come to this in a moment. So we have the pressure distributions of all the degrees of freedom which are in the game now here separated and can study them independently. Now if we look for the phase diagram itself, that means the pressure divided by the force power of the temperature as a function of T mu, what you see here on the top. We see for mu equals 0, that what we saw in lattice calculation, a very smooth crossover from low to higher pressure. But if you increase the chemical potentials, then you see the situation change slowly, but then dramatically. For chemical potential up to 0.2, we have still a crossover, but now the crossover gets steeper. And at the end of the day, if we come to still higher chemical potential, we face a first order phase transition. Now, if you look what is the phase transition localized, and you can just look at the bottom right figure. Here we have the crossover and the first order phase transition. The crossover is now it has two lines. The one is the mod temperature of the pions, and the other one is the speed of sound minimum. So it's a crossover. Is not very well defined as with one single temperature, because the degrees of freedom do not change dramatically if you increase it slightly, but it's very well defined for tapping above the 0.320 MeV. That's the first order phase transition between hadronic matter and quark matter, and this continues up to the chemical potential of 0.4. Where we finally have in the transition T equals 0, so that's the limit what we can obtain. Now you see when you come to this first order phase transition, the quarks are the order parameter. We have this typical Maxwell curve, which we can just...
George, can you hear me?
Yes?
Sorry, 5 minutes left.
5 minutes left, okay. So now the masses of the particles at the three-triangle point. When we come now to the first order phase transition, you see here in the left plot at low temperature and looking at this phase transition, we have a pion mass, which is basically constant, and then jumps suddenly at the phase transition. And we have the quark masses, which are almost constant as well, which jump down. And so we have a first order phase transition with the mass of the quark as an order parameter. Now, if you look in the three-dimensional plot of mu, T, and M for the masses of the pions and the up and down quarks, you see how this goes from a smooth behavior here, what I showed you initially, now to a behavior which is here really a first order phase transition. You see it in the quarks and you see it in the quaternions. Now, this is something which we can hope to see in experiment. For this, we have now to compare our first order phase transition points here with what is actually calculated from the statistical model calculation. And the statistical model calculation gives the freeze out surface or the freeze out temperature as a function of the chemical potential as obtained by analyzing the multiplicity of the observed particle. Now our critical point or critical endpoint is here, so we are a little bit higher in the chemical potential as the freeze out, but of course before the system gets the freeze out, it can be compressed more, and so for this reason it seems not to be excluded that in these reactions which we expect at Fair and Nika, this critical point can be obtained, and then we can look whether we see the observables of a first order phase transition. We can also go to neutron star matter, and we have done the same thing. Now we have added now for the hadronic part, because the hadronic part we have in principle to add many mesons, but it's very time consuming to do this. So we had an effective equation of state from Duchamp and Hensel, and so you see it just here, so it's a combination of NGL and this effective potential and effective EOS. And then we see the mass radius relation, which looks like this, which is basically in the bulk part of what we get with other models, as we have seen in this conference already several times. Now, the goal is not to make a hybrid model. The goal is more to combine it with more sophisticated models like from Schramm or people from the FIAS, and to make where the NGL describes the quark part and the hadronic part is described by the hadronic models. Now we can go a little bit further to non-equilibrium, and the non-equilibrium we can clarify and define by transport coefficients, which can be calculated exactly in the same scheme using the same Lagrangians, because if we go one order higher in the expansion of the partition sum in the exponent, we encounter interaction between quarks and antiquarks. And these interactions can take place either by exchange of a meson in the T channel or by the exchange of a meson in the S channel. Now we need a mesons because we have only only 4-point interaction. So these are 2 points and the 2 mesons, so the 2 quarks of the mesons are the 2 other points. So in principle, we have this kind of models here, or this kind of diagrams here. Now, depending on QQ bar or QQ, we have ST and U channel, which are taken into account. And if we calculate them, the PNGL ingredients appear in 3 different places: in the exchange mesons, in the masses of the incoming quarks, and in the Polyakov modified thermal distribution function, which are inherent in this kind of calculation. Now, in this approach, we calculate the relaxation time and the shear viscosity and the electrical conductivity to make another time contact with the lattice data. And we see here that the relaxation time decreases strongly until we come to the critical temperature, here characterized by the Mott temperature, and then it increases again in order to higher temperature. And if we have a mu which is finite, so that's mu equals 0, then in principle the relaxation time always increases. So the cross section gets smaller, we need longer time to wait until we arrive at the thermal equilibrium. And since we can now see what's happening in the transport coefficients, they are just given by this formula here and here, which contain here the relaxation time. And you see we are in principle in the bulk part of the lattice calculations, which are here displayed in comparison with calculations which we did. So it seems to be that this Lagrangian also is able to describe the transport coefficient as far as they have been obtained in the lattice calculation. Now let me come to the conclusion. I showed you a Lagrangian, the PNGL Lagrangian, which shares a symmetry with the QCD Lagrangian, even if they are global and local, and allows a straightforward calculation of finite chemical potential. So we use it to study the equation of state in the TMU plane. Now the beta-salpeter equation in the QQ bar channel allows to identify the meson as pole masses. So we have meson degrees of freedom as well as the degrees of freedom of quarks. We can also include baryon degrees of freedom, but that would be another subject which I do not like to touch here. Now we go into next to leading order in NCA and introducing an effective quark-gluon interaction. We can reproduce the lattice equation of state from mu equals 0, the lattice expansion coefficient from finite mu, and the PQCD calculation for very large mu, which makes the approach meaningful if you want to compare with quantitatively with experimental results. For this, we do not need any new parameters. The parameters are completely defined by mu equals 0. So we obtain the equation of state, we find the first order phase transition, and we are presently now exploring the consequences of this for the equation of state and for the transport. Thank you very much.
Thank you, York, for your very nice talk.
And Luis, if there are any questions, they're still not appearing for me on my screen.
Right. I cannot see questions either. If someone wants to make a question in the chat, please do so. We have a few minutes.
And yes, Jörg, this was a very good talk. Thank you.
Oh, yeah. Right now.
There is one question, you see,
Yes.
from Ankit Kunt.
Yes, okay. The question is, can phase transition lead star quakes like phenomenon? I guess it is, can phase transition lead star quakes like phenomena?
Yes, I think that is it. I mean, we explore right now the phase transition. We do not know, the problem is, we know phase transition for infinite systems, but for finite systems, we do not know. I mean, that's a very complicated subject in itself. We're just learning how to do this. And for this reason, I cannot tell you what kinds of phenomena we will see. I mean, that's a little bit too early to reply to this.
Right. There is another question, if you can answer this.
Yes, the Polyakov potential which we use, I showed in one of the slides with all the glory of the coefficients. This is exactly the equation of state or the Polyakov loop potential, which we fitted by ourselves in order to get the equation of state of the lattice calculation at t equals 0. So it's different from the equation of state with the Polyakov loop which have been published, where there are two, the one with 270 and the one with 290 MeV critical temperature. So that is something what we do by ourselves.
Yeah. Okay. So we close now the first part of the session today. We thank our speakers. Very nice talks. Please help me to.
Okay, thank you very much. Good to see you all.
Yes.
Thank you.
Thank you.
So we move now to the coffee break. 15 minutes for coffee break, and there is a video synthesis.
Yes,
Right, Cesar?
yes, I will share screen, okay?
Okay.
So we convene again in 15 minutes for the spotlight session. Enjoy
Okay.
your break.
Maybe we say to the speakers to come 5 minutes earlier, right, Luis?
One remark still. I mean, I know from other conferences that this Zoom is complicated for the question and answers. So if somebody has a question, do not hesitate to send me an email, and I will do my best to answer it.
Yeah, thank you very much.
Oh, yeah, very good idea.
Yes, and this applies for all the speakers. Please feel free to contact them.
Okay, it's on the air.
Jörg, are you there?
Yeah, I'm here.
I might ask you privately, but why do you use this parameterization for the Polyakov loop potential? Why not the logarithmic one from Fukushima?
I mean, we use it for in order to get closer to the data from the lattices at mu equals 0.
Mm-hmm.
Now, if you look for the, I mean, they both go back finally to y. There is this polynomial and the logarithmic potential,
Yes.
but both do not agree with the equation of state you have. Even if we add now the next to leading order in C, we do not come to the lattice equation of state. So for this and we looked then in the publication of Pawlowski and company, the Schaffner-Bielich-Pawlowski, who studied the change of the equation of state, the change of the Polyakov loop in the presence of quark-antiquark pairs. So they figured out that if you have in the gluon propagator a quark-antiquark pair, then the effective temperature goes down to 190 MeV.
Yes, yes, yes. So actually we also, I don't know whether you heard my talk.
No, I was not. I was busy this morning with teaching.
So we also study this, what kind of Polyakov we should use. And in the end, it turns out that this polynomial one has unphysical features. So we use the logarithmic, but it's several years ago. I forget exactly what was that. And we use the logarithmic one, but we also use that kind of effective temperature, which is different one. Only the gluon field, I mean, the SU3 phase transition would suggest. So,
yes, I mean, the point is, in principle, you have a relatively large freedom because you cannot, you have the asymptotic limit, that's for sure, because
yeah.
I mean, you get the gluon pressure from the Polyakov loop, but what's happening around the critical temperature is not very well defined. So for this reason,
yeah, of course. The question is how you can imitate the best way. So I mean, in case of SU3, the situation is quite clear, but you do not have SU3, you have quarks as well. And then it's not so clear. So of course,
yeah, for SU3, I mean, the point is without quarks, if you have the young Mills, and then all is completely clear.
Yeah. That is also what I said. SU3
yes,
is clear.
That is clear. And then is the question, what's happening if there are quarks there, as you said. And the first idea how the modification takes place was published by Pawlowski. I can send you this if you know it. And they figured out that in first order, in principle, you have a reduction of the effective
Probably we use the same method, actually.
Yeah, okay. Then, okay, that was then the next step, but that is only including now the quark-anti-quark pair from the gluon propagator. It doesn't include that the quarks are really degrees of freedom, which are there, which can scatter with gluons, all kinds of things. And for this, we took the freedom. We just say, okay, let's take a parameterization, which is then better in agreement with the equation of state of the lattice.
Mhm. Okay, actually,
Do
finally,
not-
that is the most important thing.
Yes, but that, I mean, if you look at the parameterization in what I showed in the talk, you will get it exactly in this way. You get also, I mean, the point is you have to go one order higher in NC, because otherwise the mesons do not, they makes complete nonsense. I mean, in the order NC, there are no mesons. And so therefore you give basically by quarks the pressure of the hadrons. And that is, of course, logically not very satisfying.
Yes, yes, yes.
Leading
At
order
least
in
in our
C,
quark meson model, at low temperature, all the pressure comes from, in our case, from the mesons.
yes, but that you do not get from PNGL.
Yeah, not for free.
And so for this reason, we went to the next leading order in NC, and then we adjusted in principle, we adjusted the potentials that we are best in agreement with the data, the lattice data.
Okay, so thanks.
If you have other questions, query, do not hesitate, you know my email.
Yeah, of course.
Okay, have a nice time. So.
Hello, Gabriela.
Hi, Luis, I'm here.
Very good. I think.
Ready for the questions.
Yeah.
And just in time, I did my coffee.
Yes, yes. 15 minutes is just enough.
Very nice talks. I liked it a lot.
Yes, they're very interesting.
Yeah.
I'm going to share my screen just to be sure that everything works well. Can you see my screen, Gabriela? Can you confirm that?
Yeah. Yeah.
Yeah, right. Okay, for the people participating in the spotlight session number 5, please get ready to start the session. We are going to start in about 1 minute. Okay, welcome back everyone. We are going to start the spotlight session for today. I'm just sharing the main instructions for the spotlight for the speakers. Remember that you will have 3 minutes sharply to present 3 slides. The 3 slides are already here, so I'm going to show them, and please just tell me when I need to show the next one. And please try to keep everything within 3 minutes. All right, so we are going to start with the first one. Elisa, are you there? Elisa Garcia Pereira, can you hear me?
Hi.
All right, so I'm going to show the first slide. You have 3 minutes, so you can also show your video if you wish, and please tell me when I need to change the slide.
Okay,
So
can I start?
go ahead.
All right. Okay. Good morning, everyone. My name is Elisa, and I'm advised by Professor Dimitar, and we are both from URGS. In this presentation, we'll talk to you about our research in ground-level moon flux variation in cosmic ray simulation. In this work, we examine the periodic variation of the atmospheric density as an influence of moon flux counting at the ground level and compare the simulated results with experimental data. Cosmic rays are particles that penetrate Earth's atmosphere from space, and when they do, they interact with it and create an extensive air shower. From the particles generated from the shower, one that gets the most on the ground level are moons. You can change the slide, please. Thank you. In the article, tidal frequencies in the time series measurements of atmospheric moon flux from cosmic rays from El Takai is reported the detection of tidal frequencies in the spectral analysis of time series moon's flux measurements released over the period of 8 years. The Moon telescope used in these measurements is located in New York. In this image from Taka's article, we can see an hourly average pressure corrected time series for moon data. A striking feature is the yearly modulation with maximum during the winter and minimum during the summer. This modulation is caused by seasonal variation in solar heating, and that expands and contracts the atmosphere. This change in atmospheric thickness lengthens and contracts the moon flight path. You can go to the next one, please. Thank you. To simulate a similar effect, we use the simulation toolkit Corsica. Corsica is a program for detailed simulation of those showers initiated by high-energy cosmic rays particles. It allows us to study its interaction and decay in the atmosphere. In this work, the primary particle is always a proton with energy of 10 teraelectronvolts. In order to compare to Takai's result, our simulation is set for New York, and we choose the time span of 1 year. Corsica's Earth atmospheric density variation is modeled by 5 layers. In order to, for lower layers, the density has an exponential dependence with the height, while a linear dependence with the 5th layer. All layers are parameterized by coefficients A, B, and C. In our model, we modified the density equation, including a periodic time dependence in our 4 layers, lower layers. In the figure in the left, we can see how our atmospheric model behaves for each B values at the height of 6 kilometers. And in the figure in the right is shown the simulation of for the number of moons per day in a year for different values of B. The behavior is consistent with the results presented in the figure in the left, when an increase in values of B implies a decrease in the number of moons in the middle of the year when sin square of omega t is maximum. These results are in agreement with the annual measurements of Takai's graph. The simulation was restricted to a range of 1 year due to computation time. Still, we have shown that a simple phenomenological periodic time dependence density function can reproduce qualitatively the complex atmospheric tides effects that are revealed in Takai experimental results. Thank you.
Thank you very much. Very well on time. So we have our next speaker, Lien Rodriguez Lopez.
Yes.
Can you start, please? You have 3 minutes sharp, please.
Good morning, everyone. My name is Lien Rodriguez. I am postdoc in the University of Concepcion, Chile. The title of my presentation is Influence of a Galactic Gamma Ray Burst in Ocean Plankton. There are many evidence indicating the lack of atmospheric ultraviolet shields during the Aichelin eon, and as consequences, the possible onset of high photobiological regime in the planet's surface, listing among the reasons of why continents might not have been conquered by life until the periods of the ozone layer. Thus, photobiological stand as one of the drivers of biological evolution in our planet. Radiation in general have the dual role of sterilizing non-resistant species and favoring speciation of the surviving ones, due to DNA mutation and expected availability of ecological niches. In this work, we focus on important short-term effects, the brief and immediately UV flash, reaching the ground as a result of reprocessing the gamma energy in the atmosphere. We use tools developed to model biological effects of current ozone depletion in order to do some estimate of the immediate lethality the stellar explosion or unusually intense solar flare would cause on phytoplankton. Next slide, please. Thank you. The interaction of the gamma bursts with the atmosphere has been considered. The fraction of gamma photon directly reaching the ground is negligible because of the large quantum cross-section with electrons from the molecules of the atmosphere. The ultraviolet fraction of this spectrum, 10 UV flash, is a major danger for life. The duration of the UV flash would be same on the gamma ray burst, around 10 seconds. The interaction of the UV flash photons in water and their efficiency for phytoplankton damage is our concern in this work. We use the classification of optical ocean water types originally presented in journals type 1, 2, and 3, identified as oligotrophic, mesotrophic, and eutrophic respectively. Next slide, please. To estimate the induced lethality due to gamma-ray board UV flash, we use availability data of radiation resistant as representative set of bacteria. Escherichia coli is intermediate as a strain, while the Southwest will parallel the soil bacterium Rhizobium melitoli. We find a lethality of the 10% from a gamma-ray illumination in good repair scenarios, assuming that the most species of phytoplankton would behave similarly to the aquatic bacterium Eris pharoides. Given in the poor repair capabilities, letalities of a species of genus Proctorococcus could be reached 25% even in the warm waters, and hidden at night or in the cold waters, where the repair mechanisms are additionally inhibited. Phytoplankton living beneath the mixed layer at the moment of the UV flash will not be affected even in oligotrophic waters types 1. Thank you for your attention.
Thank you very much. Very well on time. So we move to the next one. Jefferson Fortunato, our next speaker.
Yes.
So this is the first slide. Please go ahead with your talk. You have 3 minutes, shortly.
Hello, everybody. My name is Jefferson Fortunato, and I'm a master's student at the Federal University of Campina Grande. And in the present work, we provide an estimation about the performance of some future radio surveys when using fast radio bursts to perform cosmological parameter estimation. Next slide, please. As motivation, we have the fact that the fast radio bursts are an interesting cosmological probe because in its dispassion measures, we can contain information about the cosmology. And it's possible to measure the Hubble parameter from its dispassion measures from FRBs. And also, we have some future radio surveys under construction or initial phase of operation, which might provide a big catalog of localized FRBs. So we performed cosmological parameter estimation over the standard flat lambda CDM model for SHIME, BINGO, and DASCAP telescopes. For doing that, we used a set of 4 measurements of the Hubble parameter, and they were inferred from a simulated FRB samples, and we assumed that these measurements were performed by the SHIME telescope, and we reconstructed this data set along with the errors from BINGO and DASCAP telescope using the detection rates of FRBs of these telescopes using these values shown in the upper right table. Next slide, please. And next slide, please.
Sorry, there was a mistake here. It was repeated. Sorry.
I'm going to continue. As a result, we could place constraints on the standard lambda CDM flat model, and these results agree with the fiducial model used to sample the FRBs used to infer the Hubble parameter with 1 sigma of statistical confidence level. And in addition to it, we have that the BINGO telescope is a promising instrument under construction that might provide a great catalog of localized FRBs in the future. Thank you very much for your attention.
Sorry, thank you very much. We are very sorry for this inconvenience. We owe you one. Okay, let's continue with our next speaker, Vera Sinitsina.
Hello, I'm here.
Yeah, excellent. So please start. You have 3 minutes.
Hello.
Sharply.
Okay. Okay. I'll speaking about the red dwarf stars as a new source of the galactic cosmic rays, and the motivation to search for a new source of cosmic rays is that the experimental data obtained with Pamela and IMS spectrometers can be explained using the diffusive models of the propagation of cosmic ray accelerated at the supernova shocks. Next slide, please. For example, the positron fraction or unexpected rise of the positron fraction is observed by Pamela instead of the decrease of this positron fraction expected with the models. One of the explanation of this effects requires the existence of the numerous and nearby sources of cosmic ray at the distance less than 1 kiloparsec, and we consider active red dwarf stars as a possible source of galactic cosmic rays in energy range up to 10 to 14 eV. The stars are very numerous. It amounted about more than 10 to 11 stars, which is more than 90% of all stars in our galaxy. The nearest of diverse stars are the several parsecs only, and the stars can produce the stellar flares analogous to solar one, but more powerful. The estimations of the impact of red dwarf stars to the positron excess is shown with the dashed line and the green, blue fold line. And the generation of cosmic rays is to be accompanied by the high energy gamma rays. And next slide. Here next slide, please. Next slide. Next slide, okay. Here we present the long-term observations by Aichelin aimed on the searches for gamma ray emission about 800 GeV emission from the active dwarf stars listed in this table. In our experiment, the TV gamma radiation of these flare stars was detected at the energy range from 0.8 up to 10 and up to 15 eV, mostly flaring. Of type produce the flares with energy power of 10 to about 35 ergs. The flare inspector shows with black points. The searcher also the X-ray emission from the position of these stars was detected with Rosat, and higher energy emission from the unassociated object around the half of this list of these sources were detected by Fermi-Lat. And to conclude, I can say that our experimental data on generation of TV gamma rays prove that these stars are the sources of the cosmic rays up to 10 to 14 EV energies. Each of these objects can produce the flares of 10 to 34, 10 to 45 ergs each one, which is more than flares from the sun. And the estimated total energy of cosmic rays in total of all dwarf stars produced by flares of the stars is about 10 to 51 to 53 ergs, which is compared to one produced by supernova explosions. And as a result, this new type sources of cosmic ray provides the essential the positron flux additional to the one produced in the interstellar medium by interactions of cosmic rays in the interstellar matter, and can explain the rise of positron fractions observed by Pamela and IMS. Thank you.
Thank you very much. We move to the next talk. Jonathan Alexander, are you there?
Hello, can you hear me?
Yes, please start. You have 3 minutes sharply.
Okay, hello, my name is Jonathan. I am a PhD student at Pontificia Universidad Católica de Chile, and in this poster, I report the new detection of 8 candidates to extragalactic fast X-ray transients, when a subsample of them could be related with off-axis gamma ray burst. To the next one. Yeah, the motivation of this work comes from 2 previous X-ray transients detected in the Chandra-Lattice field south, especially XT2. XT2 is a transient that shows a plateau with a duration of about 1,000 seconds, and follow this plateau we have a decade. And analyzing the spectral and the host properties, this transient was associated with off-axis short gamma ray burst. So we try to find similar events hidden in the Chandra source catalog 2.0, and we detect, or we identified 8 new candidates to this extragalactic object that you can see in the panel plots in here. And some of them show similar properties that XT2. Can you go to the next one? Yeah, so additionally, we compute the local volumetric rate of our sample. that you can see in figure 1. When the red star, it's the rate of all the sample, and the blue star is it's only the object that have similar properties that Xt2. And it's clear that this discrepancy between the rate of our sample and events like shock breakout or tidal erosion events. So we can rule out the origin of these objects with these two kind of particular astronomical objects. So after that, if this subsample could be related with off-axis gamma ray bursts, when this plateau could be explained like the magnetar wind emission, it is possible using the X-ray light curves obtain the parameters of the magnetar. For instance, magnetic field and initial period, rotational period that you can see in figure 2. So the parameters that we obtained cover the range that we can expect in the case of long and short gamma ray bursts, how you can see in figure 2. And this again reinforced that initial idea that this object could be related with the gamma ray burst. After that, if these objects are related with this kind of magnetars, it is possible to use the collapse time and a sample of equation of state to try to constrain the parameters of the equation of states. And in that case, we obtain that the true equation of the states of these magnetars must have a TOB mass higher than 2.3, 2.4 solar masses. Yeah, that's all.
Yeah, thank you very much. Very well on time. So we have our next speaker again, Jonathan Alexander, a second presentation. So 3 minutes.
Okay, thank you. This is a very interesting work because this is the we analyze the supernova 1996 CR. This is the second time that it is possible to obtain X-ray spectra in high resolution of a supernova. The previous one was supernova 1987A. Can you go to the next one? So analyzing the X-ray spectra, it is possible to study the interaction of the ejecta and the circumstellar medium. So in figure 1, you have the X-ray light curve in luminosity units of a sample of supernovae 2N, and you can see that all the supernovae decrease with time. And the behavior of supernova 1996 here, it's different, increase during 5,000 seconds, and after that, it start to decrease. Very similar to the behavior of supernova 1987A. So we start to study the X-ray spectra and particularly the emission lines of this supernova. And in figure 2, you can see a close-up of two of the most important emission lines, silicon and iron. And we start to work with a non-shock thermal model, and it is clear that this model cannot fit well the shape of the lines. And also it's clear that exists an asymmetry in the emission lines of this supernovae. So we develop a convolution model where we consider that this asymmetry in the lines are related with the geometry of the interaction. And the red part of the line, it's obscured, and this obscured comes from a material that exists inside the supernova, which obscure the red part of the lines. Can you go to the next one? So with this geometrical model, we fit the emission of the supernova, and it's clear that our model fit well the continuum of the X-ray spectra and also the individual lines that you can see in figure 6. We found that exists two different components that could be explained the X-ray emission. One component one component has a high temperature and the other a low temperature. And additionally, we start to study the supernova in 8 additional epochs. We study the temperature, the velocities, and the asymmetries that exist in this. And we found that our model explained well the data at different epochs. And also we try to compare with theoretical models, and we found that you can see in figure 7, that our model also match well with hydrodynamical 1D model. So like conclusions, very quickly, it's very important the interaction of the circumstellar medium and the ejecta interaction of the supernova, and particularly this is not spherical symmetric. Thank you.
Thank you very much. So we go for our next speaker, Vera Sinicina. Can you start your presentation? Oh, sorry. Vera G. Is Vera G available? All right. So we move to the next one. Vera. Vera Weiss in China. Vera, can you hear us?
She is signed in.
Show the title so she can orientate.
Recognize us? Yes.
They are both signed in. Both this.
Hello, hello, hello.
Yes, Vera. Yeah,
Hello.
Vera.
Yes,
so
it's my.
You're
Yes,
the
but
speaker in this one, right? Okay.
yes, correct. Just a moment. Okay, Sigus-X3. Okay. Okay, Sigus-X3 as a gamma ray binary. You can switch on the next slide right now. Sigus-X3 is a famous high-mass binary system consisting of Wolf-Rayet stars and the compact objects that may be a black hole. The X-ray emission of Sigus-X3 is characterized by the 4.8-hour periodicity, which is associated with the scattering of emission by the wind from the Wolf-Rayet stars during the orbital motion of the compact object around its companion star. Also, in the X-rays, it shows long periods of high and low intensities. It is also a strongest radio source with fast and giant radio bursts. There is a link between the radio and X-rays activity of Sigus-X3 and the major radio flares occurs at the high level X-rays fluxes. Sigus-X3 has long been considered as a source of very high energy gamma rays. Next slide, please. And long-term studies of Sigus-X3 in Shalom experiment was started in 1995, and gamma ray emission was detected at energy range from 800 GeV up to 100 TeV. And for the identification of the detected gamma ray source with Sigus-X3, we perform an additional analysis to search for 4.8-hour orbital period, which is clear signature of the Sigus-X3. This is the gray area plot here. Also, it was found that the folded curves in TeV, MeV, GeV range by filling red lines here. Hard X-rays, blue line, and soft X-rays, the point, have a similar shape but shifted, except of the additional local maximum in the region of the global minimum at TeV and MeV, GeV energy range. The periods, the high and low intensity at TeV energy were found in our observation, and an increase of the TeV flux occurred during the high activity of soft X-rays and the low activity in the hard X-rays within the 6 to 8 days before the radio flares. The correlation analysis results shown in this table. The number of sequences of flare increase and low starts were detected, for example, for 2009, the example shown here. And according to the diagram of the sequences of state in X-rays and radio, the flare of the Sigus-X3 at TeV energies and Fermi-Laddite at GeV energies fluxes refer to the region corresponding to the so-called hypersoft state and the transition region before the flares. And concluding the origin of the this data, it can be said that the detected modulation of TeV gamma rays and emission and GeV gamma ray emission with orbital motion together with the high luminosity of component star of Sigus-X3 and close orbit leads to the efficient generation of the part of gamma ray emission due to the inverse Compton scattering. And the correlation of the activity of TeV energies with the flares of the stars at the radio band and delay observed between the flares and these energies could associated with the powerful mass ejected from the central regions around the black hole. Thank you.
Yeah, thank you.
Only I can say
Yes,
that one talk is missed about the
yes,
some
the previous one, this one, right?
Yes, previous one was yesterday, and today supposed to be the talk about the Perseus cluster, but it's
So the previous one listed as Vera G.
Yes, yes, it's correct, but in program is another talk.
Right, right.
Yes.
So
I can put what is what is supposed to be today? Sorry about that.
Perseus
Okay,
class.
I'm gonna put Perseus in the question and answer.
Okay, so at the end of the session, it could be.
Yeah, exactly.
Oh, thank you, thank you.
right. So let's continue. Our next speaker is Carlos Frayuca. Carlos,
Hello.
can you? Yeah, right. Can you start your presentation?
Can you see me?
Yes. Please go ahead. 3 minutes.
Okay, thank you. First of all, thank you. I would like to thank the organizer for this wonderful meeting. It's one of the best in this format, this remote format I have participated. Well, my work is in collaboration with Fábio da Silva Bortoli. We are both from the São Paulo Federal Institute in Brazil, and we in collaboration with Nádia Simão Magalhães from São Paulo Federal University, also in Brazil. The title is The Influence of Deceleration in the Shape of a Star, of a neutron star, in the breaking of pulsars. Next slide, please. What's the idea? What happens with pulsars? They lose energy as they radiate electromagnetic waves. And because of that, this energy is leaving the star, and then the star decelerates. But doing that, as the star decelerates, for the Bailerin effect, the star gets a smaller rotation, and then it deforms less. As the star is rotating, it has a deformation because of the rotation of the star. When it decelerates, this reduction of the deformation of the stars, it makes that the breaking, it's the way as the deceleration changes with time, it also decreases in time. That's the idea of this work. Next slide, please. Usually the break is equal to 3. What is the idea of the work? We got this information here. It's a sphere. It's a solid sphere rotating, and we got in the literature what will be the deformation of the sphere rotating. And it depends on some parameters, the Poisson ratios, the shear modulus, for example. The shear modulus is the G in this first equation here. Rho is the specific mass, A is the radius, and also depends on the Poisson ratio. And as we choose 0, because it's a reasonable choice, and it makes the calculations a little simple at this stage. And we got this expression, the second expression there, the delta A, the variation in the radius is of this expression here. It depends on the radius, the specific mass, the angular velocity, and the shear modulus of the star. And as we make a substitution in the expression for the...
Finish, Carlos?
Yes, I'm just saying that in the last equation.
Right.
When you got in the final expression here, the omega dot, the canonical model is only the first part, the k omega to the third. And now we got a second term here that is a correction that make the breaking into is smaller. Well, it only works for small corrections. It does, you can't make that for a big number, but that's our work, and we get a correction for the canonical model. Thank you for your attention.
Yeah, thank you. So we go for the next one by Da Silva. Daniel or
Yeah, this
Mario?
one, Daniel, yes.
Hello.
Mario? Yeah, I cannot see you, Mario. Are you available?
Danielle is
Okay.
Oh, Daniel.
on the list. There he is. Mhm.
Okay, Daniel, are you available?
Okay.
I can hear you, but I cannot see you.
I can see him now.
Right. Okay.
Okay.
Daniel, can you start, please? 3 minutes.
My name is Daniel, and my work is two-photon interaction in global production. In the last years, many exotic states have been identified in several colliders around the world. One of the exotic states providing KCD is the global. Next slide. An interesting way to investigate the hadron internal structure is through the decay width of hadrons, in particular the photon-photon channel, is interesting when we consider globals. In this work, we shall estimate the decay rates of some global candidates in 2 photons and to compare our results with experimental data. The decay rates will be obtained in the context of a non-relativistic gluon bond state model. The formalism relates the global decay G in photon-photon to the GG in photon-photon interaction, where G is related to the massive gluon and the gluon mass is about the decay amplitude for this mass process is given in terms of the helicity amplitudes by the following expression, where the function key gives in terms of Clapeyron-Gordon coefficient and the Wigner rotation matrix element. Next, please. Applying the formalism to the case of global 0++, we find the decay amplitudes and the decay width for the following process. And finally, the normalized decay width is here. The results are presented in the following table 1. Conclusion. We can see that the F0 7010 meson in table 1 is a feasible global candidate because the theoretical result is in the experimental range. The next step will be candidate the decay width to the other quantum numbers and make in mapping of the light meson sector to the application of the model. Thanks.
Thank you very much, Daniel. We are now in the part of questions and discussion.
So maybe I can share the missing slides, Luis, may I?
Yes, go ahead. I'm going to stop now.
Yeah, perfect. So I'm gonna share my desktop and visualization. So it should be now.
For Vera, right?
Yeah.
Vera, can you hear us? This is the missing talk. Vera, are you available?
She's
Vera,
still signed in,
can
but
you,
I don't see.
yes. Can you hear us, Vera? Vera, it seems that she is not available.
Perhaps her co-author, the other Vera, is still here.
And meanwhile, maybe Mariana, you can also put the slides that was missed from the other speaker.
This one from
Hello? Hello?
Jefferson. Oh, yeah. Vera.
Hello? Hello?
Hello, Vera.
Hello. It's some problem with our second computer. Sorry. Hello. May I start?
Yeah.
Yes. Oh, thank you. The objects in observations of Perseus cluster region is the title of my talk, but here I focus on the investigation of the central object of the Perseus cluster. The next slide, please. I mean the NGC 1275. It is a known powerful source of the radio and X-ray emission. In the radio bands, its structure consists of the compact central source and extended jets. The radio emission extends to large distances and show a clear interaction with the gas of the Perseus cluster. In X-rays, Rosat and Chandra observation reveals the shells of hot gas and the cavities in the gas of the cluster, which especially coincides with the radio structure extending from the central active core of exogalactic nuclei. Such structure can be the evidence of the feedback role of NGC 1275. The next slide, please. In the TV energies, the long-term studies of NGC 1275 are carried out with Shalom experiments since 1996. The gamma ray emission from NGC 1275 was detected in energy range from 800 GeV up to 40 TeV, open triangles at the spectral energy distribution. In our observations, 4 short time increases within the 5 days of TV gamma ray flux were detected, and in total, a light curve shows a slow increase of TV gamma ray flux after 2001, together with fluxes in radio, X-rays, and MeV-G fluxes. It was found that the TV gamma rays emission at energies of more than 800 GeV had an extended structure with a distinct core at the position of NGC 1275 nucleus, the grayscale image at this plot. And the core spectrum was also extracted and presented at the spectral energy distributions with the black triangles. And all the TV structure well correlated with the emission regions viewed in X-rays by Chandra, red lines here. But both TV and X-ray distribution shows a sharp decreases in intensity inside the bubbles blown by the central black hole, which is visible at the radio black lines. And to conclude, I can say that the obtained data indicate that the part of the TV gamma ray emission is generated by the relativistic jets in the very nucleus of NGC 1275. But the presence of the extended structure around these objects and the very slow rise of the gamma ray flux is the evidence of the interaction of the cosmic rays generated in the jets of the nucleus NGC 1275. Thank you for the attention. Thank you.
Thank you very well. Thank you. Excellent. So probably we can move now to the questions and answers, if there are any.
Yes. Okay. From Manuel Malero for Vera Y. Sinitsina. An investigation is underway of high energy gamma rays from SGR AXP magnetars from your collaboration or any other group. So some years ago, Fermi observed some of these sources, but the sensibility was not very high since they are at the edge of our galaxy. But recently, it was found a magnetar near the center of our galaxy. Are you aware about any recent results regarding ultra high energy cosmic rays from any of these magnetars?
Oh, if talking about the magnetars, we actually have no observations of such type source, but we should, I think, well. And if the information about the ultra high energy cosmic rays, okay, I think we should to investigate about the magnetarity energies. Okay, okay. Thank you.
Okay, and from Manuel Malero, then he puts a reference,
Oh,
link.
yes, yes, I see. Thank you. Yes, yes, thank you. Yes, I see.
So for you, okay.
Yes, thank you. It's very
Then
useful.
Rafael Diaz, good. And from Rafael Diaz, also for Vera Sinitsina, is the gamma rays emission very well directed to us, or we are actually detecting an insignificant part of the true energy emission coming out of the source?
If we're talking about the red dwarf stars, yes, it's supposed that these stars produce flares very frequent. So the part of this flares came to this to the Earth anyway, and some of these flares were detected in our experiments, if they mean this part. Okay.
Okay, thanks. And then there is a question also from Rafael Diaz, for Lian Rodriguez. Lian, you are there. The question is, are there other somewhat similar studies conducted before with which you could compare your findings, or it is the very first time the lethality due to gamma ray bursts in UV flash has been analyzed?
Oh, sorry, I not quite understand what does it mean.
No, it's for.
Oh, yes, this gamma ray emission from the red dwarf stars was detected at the level of more than 5 sigma, so significance is more than some level. So we can say that we really detect the gamma ray emission from these objects. So.
Yeah, thank you. But okay, so there was a question for Lian Rodriguez. Lian, are you available to answer? Lian Rodriguez. I cannot see her. Lian.
Luis
I
Gabriel,
think that she is
we can
connected.
also include the slide of Fortunato. This was the missing slide.
Yeah, perfect. Yes. Okay. If we find Lian, we read the question, but meanwhile, let's see this missing slide.
Probably we can give Jefferson 1 minute to explain this last slide. Jefferson, are you available?
Okay.
Yeah, please go ahead. 1 minute, please.
As I've said before, with this data set we constructed along with the errors of Bingo and ASCAP in comparison to the chimes, we were able to place constraints in the pre-parameters of the standard lambda CDM flat model. And this result agrees with the fiducial model used to simulate the FRB's sample, and with 1 sigma level of statistical confidence. And in addition to it, we have that the Bingo telescope under construction is a promising instrument that might provide a great catalog of FRBs with sources localized in the next few years. Thank you very much for your attention.
Excellent, thank you. So are there other questions in the chat?
Yes, Lian, I don't see her, right? She's no more with us.
No, she's not available, I think.
Okay, and so maybe you can send to her. the question by mail or something like that. And I see another question, but I cannot read it. You can read it, Luis?
Oh, yes, from Manuel Maleiro to Professor Carlos Frayuca. The question is, how you estimate the contribution? It was not clear. Carlos, can you briefly comment on this?
Yes, I haven't made an estimation yet because it depends a little bit. It's a little hard to find good numbers for the tier modulus and the Poisson modulus. Then we don't have estimation in numbers. It's the next phase where we're trying to find good numbers to make a good estimation. These numbers, they vary too much. And it's a little hard to get it. I don't want to get wrong estimations before I'm sure of the right parameter to adopt. Thank you for the question.
Okay, thank you.
Now
Any
there
other?
are one more question. One more question, yes? Yes. Okay, no, just a comment from Manuel Maleiro. Yes, the shear modulus, we do not know.
Correct.
Okay. One more question? No. Okay.
Okay, so, well, probably I'm the chair, but I can make a question, I guess. Sorry, I'm not writing it in the Q&A, but this is a question for Jefferson. Jefferson, can you comment about the Hubble, this H-node tension, and whether you can detect this kind of tension in your work? Can you say something about that? Jefferson, are you available?
Oh, I'm sorry.
Oh yes, this was a question for you. I was wondering about this H-node tension, and well, you are measuring the Hubble parameter at different redshifts. So, is there any indication of the tension in your work, in your estimations?
No, because we just used a few data points that were inferred from a simulated FRB's data set. So we just wanted to perform an estimation about how good these future instruments might perform when using FRBs as a cosmological probe.
Okay, thank you. All right, so we think we can close the spotlight session here. Thank you all. Thank you. I want to thank all the speakers for their participation. Please help me to thank them. So
very good. Yes.
Yeah, we are going to continue with the talk by Professor C.B. Piran at 11:30. So we have more or less a 25 minutes coffee break. I don't know if we have any announcements, Cesar, before we go to the coffee break.
If we like, we can present the synthesis.
The synthesis for the parallel stations.
If you like, I can share my screen and put it on there.
Right. Okay, excellent.
That'll be good, Benno.
Okay. So I will do it. Share my screen. Share. I think I don't need sound there, right?
Probably not.
So can you see my screen?
Yes.
Okay, so I will. So I will start in.
Excellent.
Okay.
That is good.
Can you see everything?
Yes, it's working.
Ah, perfect. Thanks.
Excellent. Stephen, can you take charge of the last part of today's session as the main chair?
Yes, I can do that.
I will be here as your co-chair. Yeah.
You can,
Thank you
you
very
can
much.
help with questions since I can't read them for some reason.
Yeah, that's strange. Yeah, but I can take that.
Okay.
The situation of our network is somehow unstable, so I'm transmitting from my phone.
Yes. Mm-hmm. Ok. Consegue me ouvir? Consegue me ouvir? Não? Ok. We're trying the best. Unfortunately, we have a generator blew up close by.
Stephen? Are you there?
Yes, I'm still here.
Can you set up a meeting tomorrow after the conference for the poster committee?
What time would you like
meet,
that?
when it ends, just after it.
What time are we going to end?
See?
Peter, I think it's better tomorrow.
Yeah, tomorrow.
Yeah, okay.
It's not tomorrow.
I can set that up on short notice. So when we know for sure, I'll put that in.
Put at 1:30 Mexican time.
That's about right. Yes.
Yeah, more or less. It's Cesar, you, Mariana, Gabriela, and me.
Okay.
Perfect. Thank you.
I will stop this presentation in 5 minutes so we can prepare for the next speaker. Okay.
Perfect.
The synthesis videos will be stopped in 3 minutes.
It's no white screen.
I stopped sharing the screen. Peter, if you like, you can prepare for the. Who's the host? Ah, Stephen is the host. Okay.
Stephen is the host. He
So
has
we
to
can prepare
announce.
for the next speaker.
Yeah. Can you do so, Stephen?
We still have, what, about 10 minutes?
Yes.
Ah, okay.
The afternoon or the morning, showing my screen. Hello.
Hello.
Do you hear me? This is Tzvi. I start sharing my screen.
Yes, I hear you.
Hi, how are you?
Yes, we hear you, and it's like you're trying to get your image. You turn your camera on.
Good to see you, Tzvi.
Yeah, nice to see you. Do you see me now?
No.
Still dark.
Still dark.
Yeah, it's still dark.
And the software shows your camera is not on, or camera is on now. It is on, so we should be able to see you. And now he disappeared altogether.
Yes. Yes.
If you could check the attendees list, he initially came on there and then I transferred him over, and my attendees list isn't showing anybody right now for some reason.
I'm already looking at it.
That we have the waiting room to test all of that.
Yes. I don't know what is going on with his camera and sound.
There's still time. Let's wait.
Yeah, that's true. We have time. Yeah, we have 8 minutes, so it's okay. We have to remember people that the panelists, that they are expected to answer the questions and answers sector, okay? They can do that. If they don't have time.
He went back. He's in the panelist now.
Okay, I will activate him again. Okay, Tzvi, now you can try again.
He's appearing without a microphone.
Because the host stopped it. I cannot stop.
No, if you check again, you should now, because you have to be activated when you first sign back in, and I've done that. And now he dropped out again. Oh, now he's back. I'll activate him again.
Maybe unstable internet connection.
That's possible.
Shouldn't be he appear with a microphone activated?
Should be, but it doesn't appear.
Yeah, maybe I think he doesn't have the microphone active.
When he was on a few minutes ago, he talked, so he had it then.
Okay.
Now he dropped off again.
I can see him again.
זה לא עובד לי. לא יודע, זה לא מתחבר לי. לא יודע, אבל זה לא מתחבר. יש לי עוד 5 דקות.
We can hear you now.
האינטרנט מתנתק. זהו.
And now we can see your image of your chair.
That his bandwidth is low.
Okay. Can you see me now?
Yes, yes, I can see you and hear you fine. You look good, sound good.
Okay, thank you. Let me open this. Share screen.
We still have 3 or 4 minutes till you begin, but if you care to share your screen first, we can check to make sure it's working.
Yeah.
And right now, of course, it is larger than what is being shown. There, that's good. Yeah, that will work fine.
You see it?
Yes, that's good.
Yeah, fantastic.
Okay, excellent. Excellent.
And you can just leave that screen there if you so choose, and then I'll just in a couple of minutes introduce you, and then you can begin.
Okay, thank you very much.
Good to see you.
Nice to see you all.
So please remember, next time in Mexico City from 5 to 11 September. Yeah?
Okay.
I'm looking forward to it.
Next year.
Well, we used to say next year in
Saturday I will
Jerusalem,
make an
so
announcement.
we have next year in Mexico City.
After my talk on Saturday, I will make an announcement.
Yeah, we are all looking forward to next year. Stephen, one question: Have you verified the list of speakers for the parallelization?
Well, what we'll do after Svi talks is we'll just start going through the list, and most of them are there. But if somebody's missing, we'll just have to go to the next one.
Okay, I'm going to spot. Missing people, and I'm going to.
We've been missing a few every day, so we'll just have to do the best we can.
Yes.
Just to inform that there's a few questions in questions and answers for Vera Sinitzina, for Carlos Frajuca, for Lian Rodriguez. So we'll have to ask them.
Any remaining questions will need to be answered in writing on the chat. We're done with the poster sessions.
Yeah, they have already been answered, Cesar,
yes,
during the session.
Yes.
We need to make them disappear from the Q&A and move them to the answer.
Yes, I will do.
Thank you.
Yeah. That's I see. Yeah, I see now.
And Svi, your screen share went big again, so you need to go back to the screen that you did have on there.
Yeah, I was disconnected for a second. I will go back to the screen. Share. And this. Okay, I hope this will stay stable.
And that is good, and it's time, and I will introduce you. Well, everyone, welcome back. This is Stephen Gullberg, and I would like to introduce our next plenary speaker, Svi Piran from the Hebrew University of Jerusalem. And he is going to talk, as you can see, about GW 170817 and other mergers. What happened? What are the implications, and what should we expect now? And with that, I look forward to having you begin.
Okay, good evening or good afternoon for everyone. Good morning to some of you. I thank the organizing committee for this invitation. I'm very glad to be. This is my third time in this Iwara series of conferences. And I'll talk about this fantastic event, GW 170817, and its implication. And this work is actually an overview that what I present here of a large community effort. Some of the results presented here were obtained by other groups, and at times I may not mention everybody, so I ask for excuse for that. And I want to recommend an excellent review paper published, but it will be published in Physics Reports by my collaborator, Ehud Nakar, on this topic. And I will begin with some very early history. So the history of this field is quite long. More than 50 years ago, the first gamma ray bursts were detected. Then we went in 74, Latimer and Schramm proposed that our process nucleosynthesis take place in mergers of binary neutron stars. The first binary pulsar was discovered actually a few months later by Jules and Taylor. Then there was an interesting shift in the gravitational waves community that took place in the 80s. There was no specific paper on that, but it's attributed to Kip Thorne. And with the shift to interferometers, which was pushed by Ray Wise and Ron Driver and others, Thorne was focusing on the shift to look, instead of supernova, to look for gravitational waves or mergers. And then in 86, Bernard Schutz suggested that we can measure H0 with these gravitational waves or mergers. At this stage, I was wondering about these mergers with the fact that we have gravitational waves, which are very difficult to measure. We have neutrinos, which are obviously will be there, but they're also very difficult to merge, to observe. We have this R process, which we have to prove that this is right. But the question is there any electromagnetic signal which is relevant that we can detect accompanying this event? And connecting this with the mystery of gamma ray burst, we suggested in '89 that all events are coming together in this merger. In '97, Lee and Paczynski added a new aspect to this, the idea of a radioactive remnant, which is called now kilonova or macronova, which is like a mini supernova that will be seen in the optical and will accompany these events. And then in 2005, we began to see the first proofs of this model, where first there was first indication of short GRBs associated with binary neutron star mergers by two independent papers by Gerholz et al. And Blum et al. And then in 2013, the first possible macronova candidate, which was identified by Tanvir, and sorry, it's Blum here, but it should be Berger. So I apologize for this typo. So this is the early history. And then we came to this event that we have now here. First, we have the gravitational wave signal. And then about 2 seconds later, we have the gamma ray burst. And actually, it was not just gravitational wave and gamma ray burst. It was the whole multi-merger phenomena. We have later on optical, which was discovered a few hours, 10 hours was the first optical detection, and infrared. And then much later on this scale, about 10 days later, X-ray, then radio were discovered. So this was a really multi-messenger phenomena. Actually, it was the second multi-messenger event. The first one was, of course, 87A, the supernova that was accompanied by neutrinos. So this was this new exciting phenomena that we are going to do, but we're talking now about these gravitational waves and electromagnetic signal, and this is what we'll be discussing here. So this is the outline. First, I'll mention some immediate physics implication. Then what did we see? Some review of the observation, very quick review. What did we see? Some interpretation of what we see, and then some of astrophysical implications, nucleosynthesis, jet physics, H0, and then the future. So some physics lessons. The first, a very simple one, the limit on the speed of light versus speed of gravitational waves. And the gravitational wave arrived 1.7 seconds before the gamma rays. And the time of flight is about 4 times 10 to the 15 seconds. And this means that the difference in frequencies of the two phenomena is less than 2 times 10 to the minus 13. A very, very impressive result with extreme accuracy on these two limits. A second physics lesson is connected with the Hubble constant. From the gravitational wave signal, we can measure the frequency, f. We can measure the f by dt, the change in frequency, and we can measure the amplitude. Now, the combination of the three can give us two quantities. One is the mass, and the other is the distance to the object. So suddenly, this is what Bernard Schutz pointed in '86. Suddenly, we have a fantastic tool that enables us to measure the exact distance to distant objects. And this is
Please mute your micros in the background.
Hello? Do you hear me?
Yes, go
yes,
on.
But there was a microphone in the background.
There was some noise in the background. Yes, I'm so, yeah, it was not me. So, so we have the frequency, the change in the frequency and the amplitude, and this gives us a distance, which is the holy grail of astrophysics. How can we measure the distance of distant objects? And here there is a precise way. And this immediately links to the measurement of the redshift, to the Hubble constant, because if we know the redshift of the host galaxy, then we can estimate directly the redshift. And this is what you see here in the top is the Hubble diagram by Edwin Hubble, and the bottom, the Hubble diagram, the estimate of H0 that were obtained by the LVC collaboration using this event. More or less at the right place, and we'll come back to this question, to this issue later. So what did we see? What are the observations? First, there was a gamma ray burst. It was short. As you can see here, it was composed of 2 pulses, 2 peaks, and it was not typical. It was very faint and very soft. Usually, short gamma ray bursts are very hard. The spectrum of the photons are very hard, but this one was a very soft one. So it was not a usual burst, and it was very faint, about 3 orders of magnitude fainter than other short GRBs. Then we saw the optical UV optical IR. This is on the left, we see the light curve. First detection was about 10 hours. It was a pity that it was not earlier, as I'll explain. Then there was a decline, and it lasted about slightly more than 10 days, then it was disappeared. And as you can see on the right, there was a complete change in the spectrum. The early spectrum was very blue, basically in the UV, and then it was gradually shifting to the red as the system was cooling, and eventually it was detected mostly in the infrared. So this was the optical story. Then we had the afterglow, and this afterglow lasted until now, almost 3 years. It was seen in the radio and the X-ray, and there was a certain moment in between it was seen also in the optical, but it mostly radio and X-ray observations. And as I mentioned before, both the X-ray and the radio began about 10 days after the burst. They were not observed right away. Then there was a gradual increase, almost a straight line, up to about 150 days. And then very sharp decline. The signal is not detectable any longer in radio, but it was detected more later by very deep X-ray observations. So at first sight, everything is very simple. We have a Newton star merger from the gravitational wave signal. We have gravitational waves. We have a short gamma ray burst, as was predicted to accompany a Newton star merger. And we have evidence for our process nucleosynthesis from the optical IR signal. So this was just what we wanted in '89. But things are slightly more complicated. So now let's try to interpret what did we see. And first, let's talk about the gamma ray burst. And before talking about this particular one, I'll talk in general about how do gamma ray bursts look, how do we understand them. Gamma ray bursts are short, intense bursts of gamma rays. They come, we know now, from relativistic jets with isotropic equivalent energy of 10 to the 50 to 10 to the 52 ergs, moving with Lorentz factor larger than 100. So the jets are extremely powerful, and the gamma ray bursts themselves are produced from the inner region of these jets, not very close to the source, from a distances of about 10 to the 13 centimeter from the source. And to see them, because of the relativistic beaming, the jet must be pointing out directly towards us. The afterglow, which accompanies a gamma ray burst, the afterglow can last days, years, days, weeks, and months, is produced by the interaction of this jet with the surrounding material. And this produces a shock wave, and the shock wave produces the observed optical X-ray and radio afterglow. There are two parts, there are two types, long ones, which are associated with collapse of massive stars, and short ones, which were believed to be associated with Newton star mergers because of this prediction that we made in '89. But this was not certain, and there was no direct proof for this idea. So these are gamma ray bursts. Now, what did we see here? The front face of this event was the gamma ray burst, this very short emission. As you can see here on the left, the signal was much weaker than typical short GRBs. What you see in the top is typical short and long GRBs, and it was about 3 orders of magnitude less energetic than a regular short GRB. If it was a regular short GRB pointing toward us, it would have been amazing in its power. And I wonder what it would have done to the detectors because it was so powerful. And on the right, you see that there was another peculiarity, which I'll come back later. The afterglow, as I mentioned, did not begin right away. There was optical emission, but it was not a regular afterglow. But the radio and X-ray afterglow began only 10 days after the event, and they were much, much dimmer than a typical event. So this was definitely not a typical short GRB, and we have to wonder what it was. A first suggestion that was actually the common interpretation, even advertised in the news release, the press release that accompanied the detection, was very simple. We saw a burst, a regular burst from the side. But we simply saw this emission of the regular burst, but since we were not looking along the axis of the jet, but from side, the relativistic beaming was not strong enough, and so on. I will not go into the details of this, but on the right here, you can see a figure by Matsumoto, Nakar, and myself that shows that the allowed region for this explanation is very far from the observed region. The observed region is on the top right of this figure. The allowed region is these 2 stripes on the bottom left, and of course there is no overlap at all. So this simple interpretation, which was very popular in the first year or so, is completely ruled out. What we do have, we must have some emission, what we have shown in this work also, that there must be some emitting region here on the side that was emitting directly to us, and it was not emitting a regular gamma ray burst. Now, there is a question what this could be, and there are many possible explanations. Our explanation is that the jet, as they propagate in the matter that surround the event, produce a cocoon, and we have here a movie that shows this. I hope that the movie will work. I hope that you see the movie. You see the jet propagating inside the matter which was ejected in the event. So the jet is getting out. And as the jet gets out, it produces a cocoon. You can see schematically the cocoon on the left side of this figure. This is schematic description of the jet, and here of the cocoon. And here you can see the cocoon building up in the movie very nicely. And this was our viewing angle. This is how we saw it. So we saw it from the side. We didn't see the jet. And this is here, more or less slightly before the time that we see the event. We have this ejector, we have the cocoon, and we have the jet here in the center, but the jet is not pointing to us. We see only part of the cocoon. So what did we see? We see a phenomenon which is called the shock breakout. And this is the moment that we saw. This is the moment that the cocoon breaks out of the surrounding matter. And this is involved in shock breakout, a phenomenon that was worked out in details by many people, but in particular by Nakar and Sari. And what we see here on the right-hand side is both the light curve and the spectrum, which is expected from this event. And as you can see here, from the light curve and the spectrum, both are resembling more or less what we saw here. There are two peaks, and in addition to the two peaks, we have also two peaks in the spectrum. We have a harder component, we have a slightly softer component, but both of them are fairly soft. So what we saw, and so far, by the way, this is the only physical interpretation that I have heard about what we saw. There are other models which are phenomenological, but this is a physical model that suggests, and with some computation that supported, the figure that you see here on the right comes out from the numerical simulation that I've shown you earlier that were done by Gottlieb. So we take the hydrodynamics and we put on the hydrodynamics the radiation transfer. And so this is and we get agreement, a reasonable agreement with both the light curve and the spectrum. So this is the most natural explanation of what happened here. But if this is the explanation, then at this stage, we didn't know what if there was a real gamma ray burst, because a cocoon can be formed on the right, as you see here, in the case that the jet managed to break out. Or a cocoon like this and a shock breakout can also happen if the jet is captured in the surrounding matter and the jet is stuck. It is possible that the jet is not powerful enough, or that the surrounding matter is too heavy, and they don't get the jet does not get out. In the case on the left, you will not have a gamma ray burst. In the case of the right, you will have one. Now we know, but I'll explain to you later how do we know it, that the situation on the right is the one, but this was only indirectly from the observation of the afterglow, not from the observation of the gamma ray burst itself. Now let's go to the macronova and the kilonova, the optical signal. This was predicted by Lee and Paczynski in '97. The idea is very simple. The matter which comes out from the merger is radioactive. It is decaying, and it is expanding. So it's something like a supernova, which is powered by a radioactive decay of nickel, but here it's a radioactive decay of other elements. And what we see in these observations is two components. There was early component, which was more luminous. it was blue, and there was a later component which was dim and red. And we believe that there were two parts here of two different compositions. The earlier component was caused by lighter material, which has a lower opacity, and the later part is done by heavier elements, which have higher opacity. And this is what brought this to the public attention, because among the several elements which are produced in our process, and I'll get back to this in a few minutes, is gold. So we have found the source of gold. We found how nature produces gold. Incidentally, even before this discovery, there were about half a dozen candidates for this phenomena that were possibly observed, but there was none that was conclusive. So this was the first conclusive evidence, and this cuts this down. Now I have to mention that from this we understand the ejecta composition of two different components. One which was lighter in terms of the elements were lighter, and the other one which was heavier. The lighter is on the left, the heavier is on the right. Two different computations by Perego, and the other one is by Bauswin. And we see here the atomic numbers that are relevant. The one on the left is due to neutrino irradiated wind coming from the disk. So even so, we didn't see neutrinos in this event directly. We saw indirectly their effect. So we have neutrinos coming from the disk, and this neutrino are breaking the nuclei and making, not necessarily breaking the nuclei, but forbidding the formation of heavier nuclei, reducing the YE, increasing the YE, and producing lighter elements. And then on the right, we have the other component, which was the dynamical ejecta, which has a much smaller YE, and this is producing the heavier elements. And from this light curve that we saw before, we know that these two components must have existed. And as you can see from the dates of these calculations, this was predicted before this event. This was not post-diction, this was prediction that we made by various groups before the event was observed. We can say quite a lot because of this about the post-merger remnant. The fact that we had a significant amount of light elements which are produced from a disk that surround the event mean that there was no direct collapse to a black hole. If there was a direct collapse to a black hole, and this is the work of Margalit and Metzger, if there was a direct collapse to a black hole, then there will be only very minimal amount of light material produced. So this must have gone through the right channel, and in the right channel, we fought some hypermassive neutron star, and this hypermassive neutron star lasted for a while. Then it collapsed for a while, I mean, a fraction of a second, maybe a whole second, but not much more. And then it collapsed to a black hole, and the final product is a black hole. And we can also rule out the rightmost part of this scenario in which a neutron star remnant was left. So we basically conclude that we have here intermediate phase of hypermassive neutron star, and then a final product of a black hole, and two components of ejecta. And this actually can tell us some hints about the equation of state of the neutron star. It cannot be too stiff, and it cannot be too soft in order to reach this intermediate channel, which is in the center. Now, this is a movie which produced by Korobkin and Roswog, and that shows the decay of neutron star matter when it is ejected to the empty space. So it's expanding and it decays, and we see the radioactive decay. And we saw that it was spending a lot of time in the neutron-rich region, and this is why it produced this final abundance that we see here of very rich by heavy elements. So it went to here, producing a neutron-rich matter, and then decaying like this. So we answered how metal produce gold and other heavy elements in this scenario. So there are some rather robust conclusions from this situation. About 5% of solar masses was produced. There was no direct detection. There was some claims of direct detection with spectroscopy, but they are not really solid. So there are no direct detection of specific elements. And this 5% are composed of 2% of low opacity and 3% of high opacity material. This high opacity material is this gold or heavy R process element that we are looking for. If we take this ejected mass and we multiply by the merger rate, and we get the cosmic R process production rate, multiplied by the Hubble time, and we see, do we have enough R process to explain all the R process in the universe? This is what we predicted in '89, and the answer is yes. This is sufficient. I'll show it in a second in the next slide. And we also from the fact that I mentioned before, there was no direct collapse to a black hole. This means the equation of state is not too stiff. And from the fact that there is a delayed collapse to a black hole, and from plus limits from gravitational wave from the formability, we know that the equation of state is not too stiff. So it is giving us some limits on the equation of state. So what we see here is how much on the x-axis we see how much mass is produced per event. On the y-axis we see the rate, and there are several lines here. This is from work by Kenta, Michael Paul and myself, and then later by Kenta and Paz Binyamin and myself. And you see that all these lines are intersecting here around a few percent of solar mass and the rate of about 100 events per mega year per galaxy, which is consistent with the GW event. So I don't have time to go to this limit. I can be glad to discuss it if there is some specific answers or questions on it. One interesting fact that came out in this understanding is the following, that in the same analysis, we understand that about 1,000 Earth's mass of gold, platinum and uranium, and maybe other heavy elements were produced near the early solar system, less than 80 million years before the solar system formation. And the question is now, so this is from this calculation that we see here. You see here the curve that I mark here about plutonium. So this is from observation of plutonium in deep crust of the sea. So we know that such event of a merger took place near the early solar system, less than 80 million years before the formation of the solar system, probably, but not much less. We have also lower limit. And it's an interesting question, again, that I don't have time to go into it. Is there life-motivated reason for a nearby merger to the early solar system? And with Bernard Schutz, we have some speculation that says probably yes, but again, this is a topic for a different discussion. So let's go now to the afterglow. This is the one description. This is the X-ray afterglow from a recent paper by Troja. You see that the last measurement was 1,000 days, almost 1,000 days after the event. This is how it is seen at different times. And of course it is fading. And you can see here only the early times. At 2 days we didn't see much. 9 days, the beginning of detection, and so on. And the peak was at around 150 days, and it was fairly sharp. So this was the X-ray afterglow. The radio afterglow is more or less similar. How can we understand it? To understand it, we have to go back to early days of afterglow to a phenomena, to the phenomena which we understood in the late 80s, early 90s, that the afterglow is beamed in a narrow beam of width 1/gamma, where gamma is the Lorentz factor. Initially, gamma is very large. So if we are looking from the side, you do not see the afterglow. You see something very big. But as the afterglow proceeds and it interacts with the surrounding medium, it slows down. As it slows down, gamma is reduced, so the emission is spread over a wider opening angle. This is what we see here at the center. So our observer who was sitting here on the side and did not see the emission initially will certainly see it later on. And this is more or less what happens here with slight deviations. So this is how we can understand this phenomena of the rising of the afterglow. And once we get into the cone, we see it like every other observer. So this is what we see here on the right side. Different observers will see different things. And what we saw is like an off-axis observer of a regular afterglow. Now from this, we can ask the question, what can we learn from this light curve? Can we figure out exactly what were the parameters inside? The answer, as you can see from this figure, this is from a recent paper that I have, is not exactly. This is, what you see here is about 10 different works that try to analyze the light curve. And as you can see, there are, for example, if we take one single very important question, what is the viewing angle that from which we looked on the phenomena? You see different values ranging from 35 to 15. So what is the real answer? And this viewing angle, as we'll come back to it, is a very important question. So this is puzzling. How come that different groups that are trying to analyze the data, these are not necessarily observers, it's the same observation, but different theoretical groups trying to analyze the same data come up with such a different results. The point is, and this is the point of this recent paper by Nakar and myself, is that just from the afterglow light curve, it's difficult to discover, to figure out what is going on. But apparently there is something else which is very useful. And this is the motion of the centroid of the image. And now I'll show a continuation of the movie that I've shown before. I hope this is going to work. Yes. We see here the afterglow formation of the jet is interacting with the surrounding medium. And on the right, on the left side, you see the centroid motion. It's like some of you are old enough to remember this movie, this computer game, Space Invader. This reminds me always of the Space Invader who is moving. But this is how an observer who is looking from the top here will see this picture. And he will see that the centroid is moving. What you saw at the center here is the afterglow light curve. So you will see that our model really goes through all the points of the afterglow. I'll show it once more. So the model goes, so the jet is expanding here. And the points go through the point of the light curve, but at the same time, the centroid that is moving on the sky, and this is the observer time. This is the observer time, how we observe. So you see the light curve is fitting here at the center, and this is the motion of the centroid on the left, and this is how it would have looked from this side. So this gives us another clue, another issue here, the motion of the centroid. And the motion of the centroid is actually superluminal. If we look at this in this simulation, it moves faster than the speed of light, just like the usual superluminal motion that is seen sometimes in AGN and quasars. So if we take now the light curve on the left and the observation by Muli et al., and also independently by Gerlanda et al. On a different, different VLBI of this, if you see this motion of the centroid, you see that the centroid moved from day 75 to day 230. And if you do a simple calculation, you find that it moved by something like 4C, so it's a superluminal motion. But now, if you take the VLBI plus the light curve, you conclude two things. First, there was a powerful narrow jet. So finally, we have an answer to the question, was there a real GRB there? Yes, the jet was very powerful. It must have escaped from the system and produced the GRB, but not towards us. And we know the parameters, and we know also that the jet is very narrow. This is why these last three groups here, which are marked in red on the right-hand side of this figure, come out with the same results of a small viewing angle and a very narrow jet. And this is the result of Otokizaka, two different interpretations of the data, and Gerlanda. These results were using the VLBI. All the other results were not using the VLBI, and as I mentioned, it is impossible to figure out what is going on without this information. So now we know what happened. This is how it looked. We saw it from the side. We didn't see the Gunnar burst, but some aliens living 20 degrees away from us would have observed the short GRB. The radio observations can also tell us something else, and this is from recent work by Ricci et al., but also several other groups. Notice that. This is the current upper limit on the radio. And from this, we know that there was not too much energy given to the ejector. In one of the previous talks, we heard about magnetars, which are very powerful magnetic sources of energy, which will give energy to the ejector and push it to very high energy. And magnetars were considered as one of the best models for producing producing gamma ray bursts, either long or short. But in this case, we have a very strong upper limit of more or less 10 to the 51 ergs. If you want to push it, then maybe few times 10 to the 51, but not much more than that, on the energy of any magnetar that was involved in this system. So depending how you want to look at it, this is some sort of a blow to this model, which became quite popular in the last few years, of a magnetar being the powerhouse that powered GRBs. On the right here, in the center, actually, you can see predictions of what we would see in few years from this event. We are waiting now for a second radio signature. The second radio signature will come from the slow ejector. The first signature that we have seen was from the jet, but the surrounding matter, the slow ejector, will eventually contribute to its own interaction with the surrounding matter, producing its own radio signal. This is something that we predicted about 10 years ago, again with the Nakar. And now we have to sit and wait maybe 20 years from now, well, 3 years have passed, or maybe another 70 years, and discover this additional component. And from this, we will learn much more on the ejector, things that we could not learn so far. I mentioned the Hubble constant, so let's get back to the Hubble constant. As you all know, I think that it was mentioned in some of the talks so far already here. There is a tension in measurement of the Hubble constant between local measurements and CMB measurements. Some are measuring between 66 to 68, and others are measuring around 74. So there is a tension, and because the CMB is a distant measurement, and the supernova is a local one, then people are is thinking maybe one has to modify cosmology in order to resolve this. So from this point of view, every estimate of Hubble constant is most welcome and most important, every independent measurement. And here we have an independent measurement, as I mentioned before, of the Hubble constant, how good it is. There is a catch here, which I didn't mention before. The catch here is that the measurement of the Hubble constant depends on the amplitude of the gravitational wave h, but this amplitude h depends on the angle, on the viewing angle to the burst. This is why I mentioned before, the viewing angle is so important. And if you're depending on the angle, we have different dependencies. So in order to actually estimate the distance, as you see here, R100 is the distance. This is actually from the original paper of Schutz. In order to measure the distance, we have to know what is f theta. And for this, we have to know what is theta. So we have to get an independent measurement of theta, and the gravitational waves themselves do not give us a good measure. The gravitational waves tell us in this case that theta is less than 40 degrees, but less than 40 degrees is not good enough. Using this less than 40 degrees, this is why these viewing angle estimates are so important, this I mentioned before. But using this estimate that theta is less than 40 degrees, then the LVC group came out with their estimate of the Hubble constant, and you can see the curve here. It's around 70, somewhere in between the two measurements, but you can see the errors are quite large, and it is not definitely a single measurement like this is not good enough to estimate, to judge between the two competing results. However, as I mentioned before, if I use the VLBI observation, and this is from the work of Otto Kezaka et al., if I use the VLBI observation, I get, as you can see here, much tighter limit on the viewing angle. And this much tighter limit on the viewing angle will give me also much tighter limit on the distance. So with this, I can improve the measurement. Now the bottom line is the LVC measurement. The upper line here is the measurement by Otto Kezaka et al. And you can see it is much narrower and the probability is now much more concentrated. So we have much better estimates. It's still not good enough, but it's a step in the right direction. So some implications of what I've seen so far. This event, GW170817, and future events like this are ideal tool to explore the jet propagation interaction on a short time scale, from birth to death. We heard in one of the earlier talks, a talk about jets in AGN. In jet in AGN, we see a fixed picture. The lifetime of such a jet is hundreds of millions of years. So we see a snapshot at a given moment of time. Here, just before our eyes, we see everything from the birth to the end. So we can study jet propagation and we can learn both about the interaction with the surrounding matter in the dense region near the source, but also in the outer region later on with the surrounding matter and so on. So this is ideal tool to explore jet physics and jet astrophysics. In this case, we know that the black hole formed, and there was also an intermediate hypermassive Newton star stage. This gives the limits on the equation of states, not too soft on one side, not too hard on the other side. We also know that the event was not powered by a strong magnetar, making some problems for the popular, too popular in my mind, magnetar model for gamma ray burst. The radio follow-up observation revealed that the core had a very narrow 4 degrees powerful jet. EISA was about 10 to the 52 ergs. but it was very narrow, so the total energy was only 10 to the 49 electrons. Knowing the angle of the jet gives us an idea on the rate of this event, because we know that the rate of observed short GRBs is about 10 per cubic gigaparsec per year, but with with opening angle of about 4 degrees, this means that they have a beaming factor of about 100, and this means that the actual rate is about 100 times larger, basically in agreement with what we know now from gravitational wave measurements. We know that we are 20 degrees, about 20 degrees away from the axis, and this has this implication for H naught. There was a jet that was powerful, and it most likely produced a regular powerful short GRB pointing somewhere else. But we don't know for sure that there was a GRB, and we'll never know for sure because we never saw the gamma rays themselves coming from the jet. We saw the shock breakout, which is a different story. Still, this is the best proof, still somewhat indirect, for the association of neutron star mergers and short GRBs. And about 5% of solar masses of rare R-process elements have been produced in this process. This is consistent with the prediction that this is the source of R-process, in heavy R-process in the universe. And finally, H naught estimate based on binary neutron star merger. If you want the estimate to be precise and narrow enough, you need a nearby bright event. Just so there were dozens of papers on how we will solve the dilemma of the H naught tension using neutron star mergers. Most of them were too fast because they didn't appreciate the need for a nearby event to reduce the error. In the last few minutes that I have, I'll talk about the future. And I'll talk about two speculative things which may be years to detect. The first one is about gravitational waves from the jet acceleration itself, some idea that I first mentioned about 20 years ago, sorry, almost 40 years ago. Sorry, no, it was not 82, it was 2002, so it was only 20 years ago. The point is, as I mentioned, that we can see here the jet from the beginning to the end, but the beginning is hidden. The acceleration process is hidden. We cannot see the acceleration process itself. Can we learn about the acceleration process? The answer is yes. We can learn about the acceleration process from gravitational waves, which will be emitted from the acceleration process itself, because we have a matter which was standing still, and suddenly it's moving very fast. And it is not spherically symmetric, it's very asymmetric. So the sudden acceleration of matter will produce gravitational waves. This will give a memory type signal. The magnitude is about 10 to the minus 24 to 10 to the minus 25. And the typical frequency, so it's not very powerful, but typical frequency is a fraction of a hertz, 0.01 to 1 hertz. This is for GW17 or 817-like events. Can we detect it? Right now, this is below LIGO, below LVC, and below other gravitational wave detectors that are operating. But there is a Japanese proposed satellite or satellite system called DECIGO, DECI from fraction of a tenth of a hertz. So this is going to, this is planned for this regime, for the future for this regime. But there are also more exotic proposal led by Stavros Castanevas, who is the head of Virgo now, proposed that I'm also a minor co-I on this proposal, is the idea to have a lunar seismic gravitational antenna, LSGA. So it will be both seismic and gravitational waves. And this was proposed to ESA, And this will be able to measure waves at this frequency band, and hopefully, one day we will measure this and we will learn exactly how the jet was accelerated. And in this case, we will not have to see the jet or even pointing to us to know that it was there. And finally, if I go back to this paper with prediction from '89 about nucleosynthesis, neutrino burst, gamma ray burst, and gravitational waves, then after all, this is the ultimate multi-messenger because it has everything. It has electromagnetic signal, the gamma rays, it has gravitational waves, but it also has neutrinos. We know that in these events, neutrino took place. Neutrino had an important role in the merger and the physics of the merger. We didn't see them directly. One day, in the distant future, with a suitable detector, we'll also see the neutrino from this event. And it is exactly 50 minutes since I started to talk, so I'll finish here. And thank again the organizer for inviting me.
Okay, thank you, Tzvi. Thank you very much.
Yes, thank you. That was excellent. And Luis, do you see any questions that we have that yet?
Yes, we have questions for Professor Tzvi. There is the first one by Manuel Maleiro. Very good talk and important. The centroid motion that you connect with the observations and with H node value and magnetar proposal that seems to be not correct. And also why we did not saw that SGRB and energy released was much smaller.
I'm not sure. Can I try to see the question?
You can see the question, yes.
The question in Q&A, the first one by Manuel.
I'll see the question. The centroid motion that you connect with observation and agent value and magnitude deposit seem to be not correct. I don't know why you think that they are not correct. And also why we did not saw the GRB and the energy release was much smaller. So let me try to explain again the point. The point is that the jet of the GRB was not pointing to us. What we can confirm now almost with certainty, based on the afterglow measurements, is the following image. And this is the relevant image here. That the jet was going in this direction. There was a regular short GRB in this direction. We were looking from here. What was coming out from here was not a regular GRB. A regular GRB was coming to this direction. This is why we saw very weak signal. And the limit about the magnetar is coming from a completely different story. The limit about the magnetar comes from the fact that this is the surrounding matter which was ejected in this event. And this surrounding matter, if there was a magnetar here at the center, was powering and giving more and more energy to this shell of matter which was expanding. And we know that there was a shell of matter which was expanding because we know that there was about 5% of solar masses were ejected. We saw it in the macronova, kilonova signature. So we know that there was matter. If there was magnetar, the magnetar was giving energy to this matter, and this matter would have interacted with the surrounding material and produced a powerful radio signal. We did not see this radio signal. And the limit on the radio rule out the magnetar. So this is my understanding of this phenomenon.
Thank you, Professor. There is another question by Jesus Rueda. What radiative processes were considered for the radio signal simulations?
For the radio signal simulation, it's basically synchrotron emission. The radio signal is produced by a shock, which is expanding into the surrounding material. And the shock, the blast wave, is accelerating electrons and producing synchrotron emission. This is a very well studied problem. Actually, the afterglow that we fitting so nicely is fully consistent with this phenomena. And also, in many cases, in radio supernova, we have seen this phenomena. So this is a very well tested model, and which is based on synchrotron radiation.
Excellent, thank you. I think that we have time for another question, Stephen. Right.
Yes, we have time.
Okay, by Rafael Riaz. Sorry if this sounds too naive, but just like the concept of a standard candle, like a type 1a supernovae, used to estimate distances to the objects, can we also expect that we may have a standard of similar kind for distance estimation, but this time via gravitational wave spectrum?
Oh, yes, this was exactly the idea of Bernard Schultz in '86. This is actually better than type 1a supernova. The idea is discussed here. We have a gravitational wave signal. We have the frequency at a given moment of time. This is the frequency. And this is the frequency at earlier time. So we have the frequency and we have the derivative of this frequency, f dot. We also have the magnitude, h. And a simple calculation tells us that the combination of the three cofactors can give us two quantities, the mass, the chirp mass, what is called the chirp mass, but it can also give us the distance to the star, simply the distance. So this is exactly like you said. Make this object like type 1a supernova. They are sort of standard candle, not in terms of luminosity, but in terms of combination. We measure 3 parameters, and from the 3 parameters, we can estimate the distance. So this is the beauty of the system. The problem is, as I mentioned, that we have to know the viewing angle, because this formula depends on the viewing angle, as we can see here. And we have to know what is theta, the viewing angle. And the gravitational waves by themselves do not give us good enough limit on the viewing angle. So here, this is one place where electromagnetic signals can help us and control what is going
on. Stephen, shall we finish here, or
was that the last question, Luis?
No, there are others.
We have time for one more.
One more. Okay, again from Rafael Riaz. From magnetars, can we expect that the orientation of ERB jets can be periodically over time, or the jets remain in their intrinsic constant orientation, leaving behind no chance to be directly observed by us?
The magnetar emission, this is another issue. It is not clear at the moment how a magnetar emission is converted to a jet, because a magnetar emission is quasi-isotropic. If you look at the pattern of a dipole, which is rotating off axis, this is the standard model of emitting pulsar or emitting magnetar, then the radiation is emitted more or less quasi-isotropically. So the question how this is collimated to a jet in a magnetar, it's a question on its own, and it is coupled to the interaction of this magnetar with the surrounding region. And my understanding of the situation is that you expect the orientation to be constant, not to vibrate, but to be not to rotate, but to be in a fixed direction.
Yeah.
Well, thank you very much, both for a great talk and also some very good answers for the questions that were being asked.
Thank you, Tzvi. Steven, I can put the synthesis of the 3 slides for the parallel sections on the area, okay?
What about them, did you say?
I can
Thank
put.
you. Goodbye.
Bye-bye.
Yes,
I can.
if you can put that up, that would be great.
Yes, okay. I will do that now, okay? Just give me a few seconds to prepare myself. Okay.
Thank you again, Svi.
Bye. Thank you.
Bye-bye.
Thank you, Professor. Very nice talk.
Very good talk, yeah. Thanks. Okay, I am sharing the screen, okay? And now I will just...
And it's just right now time to start. So,
yes.
Next we will have our afternoon, our presentations from the parallel sessions for the day. And just as a reminder to each of the speakers that you have 3 to 5 minutes to talk about your presentation that has been recorded for everyone to watch in full. And with that, having said that, our first speaker today will be Alfredo Herrera Aguilar from the Meritorious Autonomous University of Puebla in Mexico, and we'll be speaking about the general relativistic mass and spin of a Kerr black hole in terms of redshifts. And with that, if you are ready, Alfredo, you can begin.
Yeah, sure. Thank you. Well, I will present a general relativistic formula for computing the mass and the spin parameters of a Kerr black hole in terms of observational data, namely in terms of redshift and orbital parameters of some objects revolving around a Kerr black hole. This is a work done in collaboration with Raúl Lizardo Castro, a student.
Sorry, please ask me to change the slides, okay? When you need.
Okay, thank you. This is a work done in collaboration with Raúl Lizardo, a master student at UNAM, and Ulises Nucamendi, professor at Michoacán University. Next slide, please. So there is a considerable increasing amount of astrophysical observations pointing out to a strong dynamical evidence of the existence of black holes at the center of any spiral galaxy, including the Milky Way. And actually there are several dynamical systems like the NGC 4258, in which this setup can be clearly seen. However, most of the approaches that astronomers use in order to estimate and determine the mass of the black hole are Newtonian approaches. So even if they use dynamics or kinematics of several objects that are orbiting around these black holes, they estimate distances as well in a very Newtonian approach. So the aim of this talk is to propose a general relativistic method in order to estimate or compute these quantities. What we need in order to reach this aim is to compute or to measure the redshift of photons emitted by certain massive bodies revolving around the black hole. This could be gas, this could be a star, or water masers, like in the case of NGC 4258. And then we will need also the orbital parameters of these orbiting objects. So in this way, we will be able to compute to resolve an inverse problem and compute the mass and the spin parameter in terms of observational data. So when doing this, computing the mass is quite straightforward, but computing the spin is a little bit elusive because the spin is a very tiny effect. Well, next slide, please. So in principle,
you have one minute left.
Yes. When using this approach, we can derive close general relativistic formula, analytic formula, for both the mass and the spin in terms of this observational data. And a generalization of this work can be also applied to the center of the Milky Way, to Sagittarius A star. What we conclude from this work is that we need to study and see the redshift as a general relativistic invariant and not just as a velocity like the astrophysical community do. And also we'll see we will look to the impact parameter as a general relativistic object as well, and not just as a distance as actually is done.
And
so we would like to consider just more general trajectories in the future. That's all. Thank you.
Thank you very much. Thank you. Next, we have Ana Gabriela Grunfeld from CONICET in Argentina, speaking about the role of quark matter surface tension in dense compact star matter. Please, if you are ready, Ana.
Yes, can you hear me?
Yes.
Hi everyone. Let me see here the video. Yes, hi everyone. I am Gabriela Grunfeld from Argentina. First of all, I would like to thank the organizer for this amazing conference. I know the situation is very difficult for everyone, so thank you so much. So today I would like to talk about the role of quark matter surface tension in dense compact star matter under the influence of magnetic field. This work has been done in collaboration with Germán Lugones. He's Argentinian, he's working in Sao Paulo. So quark matter surface tension plays a key role in the understanding of neutron star interiors. And okay, could you please put the next slide? Yes, thank you. So finite size effects are extremely relevant for understanding the neutron star physics. So quark matter surface tensions plays a key role in the understanding of that compact stars interiors, and mainly there are three different scenarios that we are interested in. So one of them is that in the core of a dense neutron star, the density could be several times the nuclear saturation density. So then the confinement transition to hybrid star or to strange star could take place. So in this scenario, the surface tension plays a key role in the formation of that first drops. It is determinant in the formation of a mixed phases at the core of hybrid stars. So depending on the value of the surface tension, we can find a very sharp transition from quark to hadrons in the core of a hybrid star, or a mixed phase composed by drops of pasta in general, rods, lobes. Then another important scenario is that most external layers of a strange star may have a crust composed with strangelets immersed in a sea of electrons. In that, I guess I made a mistake in the presentation, and I said high magnetic field, and it is actually a high electric field in the surface of the strange star. Then it is important to include the effects of the magnetic field, because we saw, for instance, today a very nice talk of Deborah Menezes talking about that. So magnetars, they are supposed to have a high magnetic fields in the surface, like up to 10 to the 15 Gauss. So it is, I mean, it is supposed that in the interiors that magnetic fields even could be higher. We don't know actually. But then it is interesting to study that situation as well. So in this work, we studied three different scenarios. We focus on the surface tension in these three different scenarios that are neutron stars, called the leptonized neutron star, protoneutron star containing an amount of neutrino trapped in the system at the temperature of about 30 MeV, And then I put here binary neutron star measure, but actually it is a post-measure product. I mean, a compact object with a higher temperature.
We're in
and
the last minute, Anna, or Gabriela.
Okay. So please, next one. So we consider a relativistic gas with a free Fermi gas with U, D, and S quarks with magnetic field temperature neutrino caps, and we consider that the finite effects are included through the multiple reflection expansion, where here the modified density of state, it is written there in that thermodynamic integral. So we see that, I mean, in this graph at the left, we have the zero temperature, a zero neutrino chemical potential, at the left containing temperature and neutrinos. So the conclusion is the larger contribution comes from S quarks. In all the cases, the surface tension is below 25 MeV per square Fermi for very high densities, but in most of cases, the surface tension is less than 10 MeV per square Fermi. So in that scenario, the mixed phase would take place, and actually this model would support a strangelet crust in strange stars. But we have to impose global neutrality. Thank you so much.
Well,
thank you, Gabriela. Good to see you. Good to see you
too. Good to see you behind that mask.
Next, we will hear from Carlos Frajucta from the Federal Institute of Education, Science and Technology in Sao Paulo, and talking about the challenge of calibrating a laser interferometric gravitational wave detector.
Oh, hello, everybody. I hope everybody's hearing me. First of all, I would like to thank all the organizers for this wonderful meeting. It's a good opportunity in this pandemic situation. Okay, I'm here to talk about the challenge of calibrating a laser interferometric gravitational wave detector and a possible solution for that. It's a work with me and my student André Rogério Prado from the São Paulo Federal Institute and Nadia Simão Magalhães from the São Paulo Federal University. First of all, I would like to explain shortly how the laser interferometric gravitational detector works. Can you change the slide, please? Okay, in 2015 was detected the first gravitational wave event. And it works in a frequency of around 100 hertz. First of all, I'd like to show in the picture on the bottom and on the left how the detection works. It's made by interferometer. You have a laser that controls a beam splitter, divides the beam in two. You store the beam between two mirrors in each of the arms, then the laser comes back to the beam splitter again and comes to the photodetector. And then you need to set the distance of the mirrors in a dark fringe position, in a position to have a dark fringe signal in the photodetector. That's important. That's very important because if it leaves this condition, you are not going to detect anything. And it's hard to do that because each of these arms are several kilometers long, and you have a seismic vibration that moves the mirrors, and you need to apply forces to keep the detector locked in this dark fringe detection position. It's not easy to do because everything vibrates, and they vibrate in many frequencies, and you need to do that in all frequencies. And then on the bottom in the right position, we have the signal of the first detections, the 2015 gravitational wave detection. And what is important on that? What's important for me? Well, is a detection in the LIGO interferometer, and then on the left is the Hanford, on the right it's the Livingston detector. And what is important? The biggest amplitude of the detection, it was around 128 hertz. In this one and the other detections, the frequency is around 100 hertz. That was important. And we have, before the laser interference, we have other detectors that were the resonant mass detectors. And they didn't detect anything because of historical reasons. They adopted the bar form for the resonant mass. And it's a little hard to do that because to set the frequency, the operational frequency, you have only the degree of freedom of the length. With a 3 meters long bar, we detect a signal of 1 kilohertz. To have a detection in this frequency, 100 hertz, the bar must be 30 meters long. That's the reason they didn't detect anything, because they have a network of detectors that operate for almost 1 decade and no signal was detected. But the operational frequency was 100 hertz. Can you change the slide, please? And then our idea is to, well, in my exposition, you can see why it's difficult to keep the laser locked in that position. But something we can do is to mount in the same position, in the same direction of the detector, mount a gravitational wave detector, a resonant mass detector that will detect the same signal. And this detector is very easily calibrated. It's straightforward to calibrate. You send a signal to the mass, and you measure in the transducer the signal, and it's very easy to calibrate. What didn't happen in the laser because of the locking, you can't send a signal to calibrate the laser interferometer. And we make this calculation with some parameters. It's a new shape of the detector. It's like a tuning fork. And you have two degrees of freedom. You can change the masses that vibrate and the spring, the arm that connect the masses. And with that, we got the sensitivity curve here on the bottom on the right. And it touched the LIGO sensitivity curve. Thank you for your attention.
Well, thank you very much. Thank you. And next we were going to hear from Karin Menendez, but she is not present. So we'll move on to Luisa Jaime at the Institute of National Investigations Nuclear in Mexico. Speaking of cosmic inflation without inflation.
Yes, hi. Can you hear me?
Yes.
Yes, perfect.
Perfect. So I am Luis Jaime. I am from the Instituto Nacional de Investigaciones Nucleares in Mexico. And I am going to talk about cosmic inflation without inflaton. That is a new theory that we are proposing in order to explain the evolution of the universe and some other things. And in particular, I am going to talk about the inflationary prediction of the theory. This is the result of these 4 papers that you can see there. They are all published already. And it's a collaboration with Gustavo Arciniega, Pablo Bueno, Pablo Cano, Jose Edelstein, Robbie Hennigar, and the last one with Gabriela Piccinelli. Please, the next slide, please. The next slide, please. Cesar?
Sorry.
Yeah, it's fine.
It's okay.
Yeah, thanks. So the theory that we are proposing consists in adding curvature corrections into the Einstein-Hilbert action. It could be seen like a generalization of the Lovelock theory. This theory has very nice characteristics that make us Einsteinian. Its vacuum spectrum solely consists of a graviton, the standard one, and it's a theory that is gauge-free. This was shown in the papers that are mentioned there, not in these 4 papers that I put in the first slide, but in other ones. And the black hole solutions are Schwarzschild-like. So these characteristics are very nice for a modified gravity theory. And in the papers that I mentioned, we show that the cosmology is well posed as an initial value problem. The field equations are second order, and they can provide latent cosmology as close as we want to general relativity. And at the beginning of the universe, they produce an inflationary period that is gracefully connected to late time universe. That it is also a very nice characteristic. And in order to see how well is the inflation, the inflationary period in this theory, we compute some predictions for the theory in order to have something to compare with observations. The next one, please. So I just wanted to show you here the generalized Friedman equations for this theory. They are very nice. They are second order. You can choose the dependencies. This f of h is a function of the Hubble parameter that can be seen like this series. The thing with the theory is to choose wisely the coefficients in this function. So if we choose wisely the coefficients in this function, we can produce an accelerated behavior at the beginning, but not just that, we can make it exponential. So finally, I just wanted to mention here these two plots. This is the age of the universe compared with general relativity. It's pretty much the same. And except at the beginning of the universe. In general relativity, you cannot have acceleration, but in this theory, you have these characteristics at the beginning of the universe that makes the universe to accelerate. So we compare by using the slow roll approach, the predictions of the theory in the standard plot R versus NS, and we found these predictions for the evolution for 50 to 60 eFols. And we can see that they are in a very good agreement with observations. So that's it. If you have any question, I am available. You can write me an email or thanks.
Thank you very much, Luisa. Thank you. That was very good. Our next speaker will be Marcos Garcia from Institute for Theoretical Physics at UAM in Spain, speaking about reheating and post-inflationary production of dark matter.
Yes. I am assuming you can hear me, so thank you all for listening to my contribution. You've heard the title. This work has been done in collaboration with many people who are properly acknowledged in the actual recorded talk. Sorry for not showing them here. And so as described in the abstract, our goal has been to perform a systematic analysis of out-of-equilibrium dark matter production during reheating, and to try to exploit dark matter as a probe of the dynamics during the very early universe. Can you go to the next slide? Next slide, please. Sorry, I don't see the next slide. There's the next slide. Okay, good. So as it's written there, inflationary reheating was a stage of very rich dynamics. The evolution of energy densities and therefore of temperatures does depend on the shape of the inflationary potential and on the couplings of the inflaton to matter and radiation. So in this example, we show how for the same coupling of the inflaton to fermions, a quartic potential and a quadratic one lead to very different time evolutions for temperatures during reheating, with the maximum temperature being almost independent of the potential, but with a reheating temperature that is much lower for flatter potentials. Not only that, but the decay products of the inflaton are produced initially in a very non-thermal state with distributions peaked at energies of the order of the inflaton mass. And it is only after splittings and scatterings become efficient that they evolve to the thermal equilibrium state. And so before thermalization, particle production from scatterings can be significantly enhanced relative to thermal scatterings. So our task is then to find if these dynamics leave an imprint on dark matter. Can you go to the next slide, please? And of course, the answer is yes. At least it is in the case of feebly interacting models where cross sections are suppressed by powers of some UV scale, which is denoted here as lambda, or in the case of direct production from inflaton decay. So when this is the case, relic abundances do become sensitive, as I mentioned, to the shape of the inflaton potential and the time scale of thermalization. And it turns out that if you ignore these effects, you can be led to underestimation of many, many orders of magnitude in relic abundances, at least. Now, of course, due to the feeble interactions of this kind of dark matter, the search for the imprints of these dynamics needs to be through indirect detection. Either, let's say, on the spectrum of their decay products, like photons or neutrinos, let's say through Fermi or ice cube detection, for example, or on deviations from standard WIM predictions for structure formation. In this case, at least in the case that I talk about in the actual recorded talk, quantified through constraints on like dark matter masses from Lyman alpha observations. And these deviations can be of many orders of magnitude. So if you want to know more, please have a look at the complete parallel talk. Thank you.
Thank you very much, Marcos. Thank you. Our next speaker will be Mario Luis Lopes da Silva from the Universidade Federal de Pelotas in Brazil, talking about strong decay of hybrid mesons.
Hello. First of all, I'd like to thank the organizing committee for giving me the opportunity to talk to you. I will talk about the strong decay of hybrid mesons. This work was motivated by recent discovery of exotic hadrons, like as pentaquarks by the HCD experiment. Other important motivation was the beginning of operation of the GluX experiment at JLab that is looking for exotic states, like as hybrid mesons. The existence of the exotic states provide an important test for QCD because these states are predicted by existence by QCD. Next slide, please. Here we use an effective Hamiltonian model to calculate the decay rates of hybrid mesons to usual mesons and compare our results with experimental data. The candidates we consider are Pi1 1400 and Pi1 1600 with quantum numbers 1 minus plus, which are exotic quantum numbers that are not possible for usual mesons. Here we have the experimental results for these candidates. Next, please. We try to adjust our results to experimental data for both candidates. For the Pi1 1400, it was not possible to describe the data for total width. We find around 22 MeV, and the experimental value is 330 plus minus 35 MeV. Then our results indicate that Pi1 1400 is not a hybrid meson. If there are no other decay channels which are not detected yet. For Pi1 1600, we can describe the existing data. Our results for the total width is around 217 MeV, and the experimental results is 257 plus minus 60 MeV. This result opens the possibility of the Pi1 1600 to be a hybrid meson. Thank you for the opportunity.
Thank you very much, Mario. Next, we will hear from Nadia Magaha, excuse me, I'm sorry.
It's okay.
From the Universidade Federal de São Paulo in Brazil, talking about angular momentum conservation and core superfluid dynamics for the pulsar, J1743333. Please begin.
Okay. Thank you very much for the opportunity of participating in this great conference. I'm going to present part of the PhD thesis of my former student, Heitor Oliveira, regarding this angular momentum conservation. And for, please change the slides. And I'm going to talk about pulsars, a specific group of pulsars for which we have the second time derivative of its pulse very well measured. And the canonical model to explain the blinking of the pulsars basically assumes that it's a star that is rotating rapidly. It is highly magnetized, made mostly of neutrons. It beams light in analogy to a lighthouse, and it would be slowly spinning down as the outgoing radiation carries away rotational kinetic energy. This is what we call the canonical model. And from this model, there is a quantity that is called the breaking index, which is calculated with the parameters that are observed. And according to the canonical model, this number is always 3. But for the actual measurements, the breaking index is never equal to 3. Actually, it's less than 3. And the smallest one of them is nearly 1, 0.9, which is the breaking index of this pulsar that I'm going to talk about today. Well, and we went to study the interior of neutron stars. And as neutron stars are assumed to be made basically of neutrons, a superfluid of neutrons that rotate very rapidly. From classic fluid mechanics, a superfluid that rotates very rapidly would produce vortices in its substance. So we assume that this would happen as well in stars, and in fact, it is assumed to happen in stars too, in neutron stars. And with this assumption, we investigated how these vortices would change the moment of inertia of a star. So we did the calculations assuming that the star would change moment of inertia simply due to the motion of the vortices, superfluid vortices. And we assumed as well that the change in moment of inertia would be very simple. We have used a simple mathematical expression. And from this expression, we calculated the power that would be emitted from the star. And we also calculated the breaking index in our model. And from this breaking index, we invert the equation and find the mathematical parameter that we need based on our model. And this mathematical parameter that we obtain for the different pulsars, it has the same order of magnitude of the velocity of the vortices inside the star. So it's very compatible with this idea. The rotation and angular momentum then are correlated in our work. Please change for the third slide. This is the first one, and the third, please. Yes, thank you. And then we calculate also angular momentum. For this pulsar, which has breaking index close to 1, angular momentum is conserved. And then we find our mathematical parameter that relates to the angular momentum. And we conclude, left. Sorry?
1 minute left.
Okay. And so when angular momentum is conserved, the mathematical parameter that describes the change in moment of inertia, it coincides with the velocity of the vortices in the neutron superfluid. So we find that the motion of mass inside the star should be considered in the study of the breaking index, which in turn relates to the blinking of the star, the rate of blinking of the neutron stars, which is still an open problem. So we have these conclusions that we model changes in the moment of inertia, and then it would change due to mass motions inside the star, which is quantified by the displacement parameter. And we found that this displacement parameter relates to the velocity of the superfluid neutron vortices when the breaking index is near 1. And then for young solitary pulsars, the inner mass motions may contribute for the observed values of the breaking index. These are our main conclusions. And thank you very much for your attention.
And thank you very much. Next, we will hear from Pradyum Sahu at the Birla Institute of Technology and Science in India, speaking of energy conditions and non-minimally coupled FRT gravity.
So, hello everyone, I think I'm audible. Yeah, so thanks for the organizers to giving the opportunity. So this is the work with the collaboration with my students, Mr. Sanjay Mandal and Simran Arora. So I'll speak about the energy conditions in the non-minimally coupled FRT gravity. So basically, we consider the FRW metric with a perfect fluid matter source. And the theory, we have taken a modified gravity called FRT gravity. Can you go to next slide, please? Okay. So the main questions in this talk is basically one can go through the details in the recorded video. So here basically due to the difficulties in general relativity to describe about the initial singularity problems, then cosmological constant, flatness problems. So these are some problems which are there in general relativity. So people consider many alternative gravities to overcome that. So one of them is the FRT gravity. So the FRT gravity has 3 forms, which was given here. So in this talk, we have considered the third form, which is called the non-minimal coupled gravity, because it is coupled the geometry in terms of the Riccati scalar R and the matter content of the universe in terms of the trace of the energy momentum tensor capital T. Okay, so this FRT gravity, if you go for the formality R plus alpha T. So we have taken FRT is equal to R plus alpha T, where alpha is the free parameter. And when you consider this alpha is 0, then this FRT gravity will reduce to general relativity. So it is very easy transformation from FRT gravity to general relativity. So one can compare easily the FRT model with general relativity, and what about the difference between the two models. And in particular, we have considered here the energy conditions, the null energy condition, weak energy condition, strong energy condition, and the dominant energy conditions. And as you know, in general theory of relativity, these energy conditions are the Aichelin equations, and this describes about the black holes, wormholes. If you go for the Penrose equation or Stephen Hawking's black hole, so these energy conditions are used to describe this. And in particularly in GR, what we used to do, we used to describe these energy conditions, in particular the strong energy condition, which says that the violation of strong energy condition indicates the present acceleration of the universe. Next slide, please. Yeah, so what we did in this article, we framed the field equations, then we wrote the energy density and the pressure in terms of the Hubble parameter and the deceleration parameter. Then we consider the values of present Hubble parameter H0 is 67.9 and the present deceleration parameter is minus 0.503 from the Planck 2018 data. Then we plotted the figures of the 4 energy conditions for these values of the free parameter alpha. Then we saw that this null energy condition, then weak energy condition, and the dominant energy conditions are validated in this theory, whereas the strong energy condition violated, which is given in this graph, the first graph, and the other 3 graphs are there in my detailed talk. Then after doing this, then we compared our model with the standard lambda CDM model. And when you go for the equation of state parameter omega, which is P by rho, then we derived the values of P by rho the equation of state parameter omega, and for the same range of alpha, we verified that our model reduces to lambda CDM model. As you can see from the second graph, this omega is approaching -1 near to very small values of alpha. So yeah, I'm concluding. So clearly we gave that here that the strong energy condition is violating, indicating that it is the model is as per the current acceleration, which was given by Matt Visser in 1998 article. And this is due to the violation of strong energy condition, where all the rest 3 energy conditions are validated. And we showed that our equation of state parameter is approaching to -1 for the particular values of the free parameter alpha, indicating that this model is reduces to lambda CDM model. So thanks for your patience and thanks for the opportunity to give me.
And thank you for your presentation. Now we will hear from Sergio Horas from the Universidad Federal Rio de Janeiro, talking about thermodynamics on FR theories.
Hello, good afternoon. Can you hear me?
Yes.
Yes. Okay, yes. Great. Thanks for having me here and congratulations on the workshop. So this is a work done with my PhD student, Cesar Peralta from University of Antioquia in Colombia. So in this work, we study f of r theories, and it's well known that you start in the Jordan frame, where we define this nonlinear function f of r, which would be just plain r minus 2 lambda for Einstein-Hilbert gravitation theory. And then you can, through a conformal transformation, go to the so-called Einstein frame, where you end up with a Lagrangian, which would be this just mu Ricci scalar plus an extra scalar field. So in this work, we follow the same path, but backwards. We start in the Einstein frame with a particular potential of just plain phi squared potential and investigate the f of r that comes from this potential. So next slide, please. So in a nutshell, we will start in Jordan frame, as I said, with f of r and make a conformal transformation. And at the end of the day, you have an Einstein frame with a different metric, this G superscript E. So we have a Ricci scalar defining this metric, and we have a phi field, which materialize this extra degree of freedom that is in any f of r theory. And this phi field is subject to a potential V sub E, which is defined in the fourth line, okay? So we start, as I said, assuming a plain phi squared potential. A is just for the sake of completeness, there's a shift in the vacuum, and we just add an ad hoc cosmological constant here, which will be really interesting in the next slide. But for now, we can solve this equation. Actually, the work done which did that in the first place is written on the right side margin. So it's not our work, but you can write f and r as a parametric function, right? So we can see here that when phi is really far away from A, from its vacuum, it's slowly rolling downhill. So we have inflation in both frames, in Einstein and Jordan frames. And f, if you write as a function of r, is going to be approximately r to the 2.2 power. It's not r plus r squared, it's just plain r to the 2.2 power, okay? So it's similar to Starobinsky, but not quite so. And when phi goes to A, then we have f as a linear function of r. So we go back to general relativity when inflation is done. So what happens in between is what is really interesting. So next slide, please. So we identify here, the lambda that we added in the previous transparency as an effective temperature. We identify F as an effective pressure, and we identify the Ricci scalar R as the Gibbs free energy. And why is that so? Because when we do that and we plot G as a function of P and T, we have this 3D picture on the left, on the top left corner of the transparency, which is really exactly what happens to a van der Waals gas. So that's a third description. This is not an effective curvature fluid in either frame, nor Jordan, nor Einstein frame. This is a third interpretation. So we can have these thermodynamical quantities temperature, pressure, Gibbs free energy, and we can define the volume as well. So we can plot the pressure as a function of the volume, so we can see exactly what happens in a no-ideal gas, and we can calculate and we can plot the binodal and the spinodal lines. So the system starts when the phi field is really far away from its vacuum. It starts with a large volume and goes, it's being compressed, so it crosses the spinodal line and then ends up close to the binodal line on the left-hand side of this PV diagram. So we can go further. We can plot in the lower left corner of the slide the specific heat. So for lower temperatures, it diverges, and for higher temperatures, it does not, just like in the first order phase transition. And in the bottom right corner, we can plot the entropy as a function of temperature and pressure. So we can map the binodal and the spinodal lines onto this 3D plot as well, which is exactly what we want to get in a first order phase transition. We can use catastrophe theory to understand what is happening here. But the punchline is that it's not just a coincidence, because we can plot
1 minute.
the effect. Sure, thanks. We can plot the effective sound speed squared. It's the middle plot, the bottom line, as a function of time, as long as the phi field is rolling downhill, for different values of the temperature. So you can see inside the red circle, that's a region where the sound speed squared is negative, which means the system is unstable. So we can see that this region, can show that this region matches exactly the region in the first picture where the second derivative of f is negative, which is already known as a condition for instability of the f of r theory. So this is a new approach, and we're studying consequences of this approach. Thank you.
And thank you very much.
Thank you very much.
Well, this today will conclude our parallel session speakers, and we'll now open up for questions. I just want to remind everybody, if you have questions, to put them in the Q&A, and then also be sure that you address the question to whom you intend it to go to.
Yes, there are some questions, Stephen.
Well,
yeah, there are some.
And please, please start then, Luis.
Yes, from Manuel Maleiro to Gabriela Grunfeld, how you introduce the surface quark matter tension in your calculation to study the quark-hadron phase transition in hybrid neutron stars. Could you comment on that?
Yeah,
Gabriela, yeah.
Of course, thank you. Okay, you can start from a Fermi gas model with or without magnetic field. That is on your choice. So if you include magnetic field, you can start from a Fermi gas like that presented by Strickland, Menezes, and Aichelin. Then you have a thermodynamic potential. In that thermodynamic potential, you have a thermal integrals, and in that integrals, you replace the density of states for that of the multiple reflection expansion. That depends on the mass, on the size, volume or radius, and on the momentum. Then you will see that that thermodynamic potential parallel perpendicular if you have magnetic fields, if not, it's only one. They have the thermodynamic potential has two contributions. One, it is proportional to the volume, and the other one, it is proportional to the surface. If you only consider surface, you can have curvature as well and other terms. But the one proportional to the volume is the pressure, and the one proportional to the surface is the surface tension. So now you see that it is no longer that the thermodynamic potential is minus the pressure, because you have another term proportional to the surface tension. So then you have the surface tension, then you have to impose global neutrality, no longer a local neutrality. Then you have to consider the surface tension of one phase embedded into the other one, because you can have quarks embedded into the hadronic sea, or the opposite, or you can have hadrons in quark matter. So then you consider the surface tension of both phases, and then you have to consider thermal and chemical equilibrium through the Gibbs free energy per volume, that it is the same value for both phases. So that's the way you introduce it. I hope that answered your question.
There are
Thank
more
you, Gabriela.
questions.
Yeah,
we have more.
Yeah.
Please.
Yes, we
Luis,
have more.
Luis,
Yes,
there is at least 2 questions in the chat also.
yes, I'm going to read them. Yeah. To Luisa Jaime, is there any disadvantage of the theory of H? Luisa, would you like to comment on that briefly, please?
Yeah, sure. Well, yes, of course, it should be. I mean, general relativity is a very elegant theory. It has a lot of properties and nice properties. So what we are trying to do with this proposal is to rescue all the possible things that makes general relativity so beautiful, right? So, but at the same time to explain some other things that general relativity cannot do it. So we are trying to do that. These very nice characteristics are for maximally symmetric spacetimes. So if you change that, the field equations will be for order and they will have expressions more longer and that kind of things. Because we have, of course, the Lovelock theorem, and we will have for order equations if we broke symmetries. For example, we are studying also stars, or well, spherically symmetric the ansatz with matter, and the solutions, the field equations are for order, and there are some other things that one has to analyze. So of course, it will have some disadvantage, I suppose, but this theory in cosmology has just about 1.5 years, and the first predictions that we have is right there with the inflationary predictions within the constraints of Planck. So I think that it is a very nice theory that it worth the time to dedicate to the theory. So yes, I suppose that it will. Yes.
Thank you, Luisa.
I have another question from Sergio, but he made it.
Yeah. Yes. We will give room for that. Let me try to follow the list that I have already here. Thanks. Sorry, I forgot to mention that the question was by Namjoon Lee. Another question by Manuel Maleiro to Nadia Megalaes. Very interesting. If I understood correctly, you show the change of the momentum of inertia for that specific pulsar. So Nadia, would you like to comment on this briefly, around
Yes.
1 minute or so?
Yes, okay. Actually, I think that he continues in the next line, that the specific pulsar comes really for the vortices formed by superfluidity. Yes, Maleiro, you are correct. The idea is that the motion of the vortices, they contribute to as an angular momentum reservoir, if we could say that, you see. And so that when radiation is emitted from the pulsar, that energy, it doesn't imply that the rotation energy is going to slow down quick as in the n equal 3 case, but because there is superfluid inside which is rotating, there's angular momentum that keeps the system going. And we showed here the case of this pulsar, which has breaking index equal to 1, which has angular momentum conservation. But we also studied the other pulsars, and they have different aspects that have to be considered as well. But what you mentioned in your question is correct. Thank you.
Thank you. So as Luisa mentioned, there is a question Sergio Juras. He's also one of the speakers, so he couldn't write that question in the Q&A chat. but I'm going to read it anyway. If I guess that we still have.
Yes, go ahead. Your signal was interrupted, Luis.
I can make the question if he has some problems.
Go ahead, Cesar.
It's from Nayung Lee, and the question. Yes.
The one that is missing is the one from Sergio Horaz.
Yeah. No.
Not
No.
yet.
I think this is also missing, no? Because this is the Luis. No, this was the first.
Yeah.
We're going from.
That's true. Yes. So I have to change again here. Yes. Okay. From Manuel Malheiro to Pradium Sarro. From where comes the condition that the ρ plus 3p needs to be positive if in cosmology we have exotic fluids with negative pressure as dark energy? Could you comment on that, please?
Yeah, basically this ρ plus 3p is the strong energy condition. So if you go for the dark energy part, then the strong energy condition must be violated. And if you think about the positiveness, then the positive potential can violate this condition if you go for a scalar field. So the observations of dark energy or the cosmological constant, it shows that the strong energy condition fails to describe our inverse.
Okay, thank you. Please, Steve.
Yes, I think that we don't have any more questions.
Oh, there was the one that was in the chat from Sergio for Luisa.
Yes, Yes, I'm going to read it. Let me try to find it.
May I read it? I have it here in front of me.
Yes, go ahead.
The question is to Luisa Jamie. Can you comment on the long-term cosmological evolution, such as radiation and matter-dominated eras?
Yes, thanks. May I share my screen or not?
Yes.
Yes, thanks.
But let's see, let me get Cesar's screen out of there first. Oh, you got it, okay. Is this what you needed?
Okay.
Here you go.
Can you see it? My screen now?
Mm-hmm.
Yeah. So what I understood is you wanted for me to comment about the evolution of the domination for different time of matter and radiation and that kind of things. In this plot, I am showing the evolution of radiation, matter, and dark energy associated to the cosmological constant under GR and under this model. It is not very clear because it's very tiny, but I am trying to show better. So the evolution, the solid line that is behind the dashed line is general relativity for this for the top of these plots, and you can see that it is basically the same. We have a proper matter domination epoch that will allow two galaxies to form, and it will be pretty much as general relativity. That's why we say that it will be as close as we want to latent universe in GR. And in this other plot, I just put the cosmological constant equal to 0 in order to see how important it is for this theory. And we can notice that it is as important as it is in GR. So with this theory, we are not avoiding the presence of the cosmological constant, but we are providing some a different kind of explanation for this, for the presence of this zero order into the action. And many other things that, inflation, graceful exit, and some other things that the theory can explain. So the evolution of the components of the universe is very close to, is basically the same that we have in GR. And that's it. That's my answer.
Thank you very much.
Mm-hmm.
Is there anything else, Luis, Cesar?
No, I cannot see any other question. They have been answered.
Well, that works out well because we're right on time.
Yes, that's true. But we have no questions in the chat and the QEAA. Let me see.
Before we say goodbye today, Cesar, do either you or Peter have any extra comments before we adjourn?
Yeah.
Well, maybe Peter would like to say something. Yes.
No, for today not. Only that tomorrow the POSA committee will meet. No, that's everything. That's all.
Yes, after the last talk, yeah.
Session. So Stephen will send us an invitation, I suppose.
Yes, after the last panelist, yeah.
Yeah. But it looks good.
I would like to say yes. What a great day it was. We had just some terrific speakers today. I enjoyed everything in each category.
All problems I suppose will happened, but we found out an easy way to resolve them. All this
what I have to say is that the cell phone, handy, works fine as a source for the signal for the internet, because we are both here working with a lot of computers and everything worked fine at the end.
You have no connection to internet?
No, now I have.
It's fine now. It's fine, but it was
recommendation next time you don't destroy the electricity.
Whoa. Maybe Beno did it. You see?
Anyway, then I thank every one of our panelists and attendees today, and I hope you all enjoyed the day as much as I did. And we will conclude for today, but look forward to seeing you all again when we begin tomorrow for us in Mexico City time in the morning, but for time it happens to be where you are in the world.
Yes, that's true.
I like only comment on if someone in the panelist will do a question. We can make a space for this that they can ask themselves because they are co-host. What do you think about that?
Yeah, that's a question we can ask it. We can take a question from the question and answer section, then ask somebody from the panelist, and then go over to question and answer section again. I think that's the best, instead of looking in the chat where the questions are, because there are all the other information.
Yes.
That's right, yes. This was only my only comment,
We're learning more every day.
Yeah, that's true.
Training on the job, yeah.
No doubt about it. Today was a great day for us, for Ben and for me. We learned a lot today.
Very good.
No, it was impressive to see how the handies, what capacity they have to compensate if the internet went down. They can compensate it. This was very interesting to see.
Incredible. This was a perfect solution you found.
Yeah.
Okay.
Of course, we should spend a lot of money on that, but no problem.
So see you, no?
You
I will leave you.
It worked.
Tomorrow.
Bye.
Bye-bye.
Bye-bye.
Luis, tomorrow we will share together the moderator, right?
Yes. Let's convene tomorrow early in the morning.
Yeah.
Oh, okay.
Yeah.
Tomorrow is your turn.
I will be ready at 7:30. Yeah, I will be ready at 7:30 tomorrow.
Okay, very good. So let's talk tomorrow. Hopefully our internet is fine tomorrow.
Hopefully so. Yeah.
And if we wanted to, it looks like our panelist list is narrowing down. If we want to also narrow down the attendees list, I'll have to transfer host to one of you to do that, because once again, I can't see the attendees list for some reason. So I'll send it over to you, Luis, and then you can remove the attendees and just come back and activate me again.
All right.
So you are now the host.
The host. So I need to remove the attendee.
Go to the attendees and remove them, and then we can continue our staff.
All right. Okay. So I have to do it one by one, right? I haven't, done this
that's the only way I know so far, one by one.
Yes, I think so, yes.
Fortunately, there's not too many that are still there.
Just to talk with you, Luis and Benno, I am a little bit late today with so many problems. So I prepared the material. I will send to you, okay? The program for tomorrow, okay? Just give me a few minutes, okay?
Okay.
And Benno and Stephen, I would like to talk to you, not today, but we can define one day to continue our article, yes?
Yes, I was just thinking about that too. We need to do that.
Yes, because we have to prepare at least a version for the others, yeah?
And it is in good shape. There still needs to be a little more added, but we're well on the way.
Okay, I think so, yeah. As soon as you finish your part and send me back the material, we can try to discuss a bit to finish, yeah, to polish.
Now I
to
have more,
polish.
now I have more time for that because I was working on my presentation up until we started on Sunday.
Okay, we can polish a bit, and then we can send to the others, to Monica, Jorge, Milton, yes?
Yes. So the attendees are down to 0. We have 6 panelists. Fia is still with us, and Luis, you can either make me the host or a co-host. I'm just me right now.
Right. Right. Let me find you. Yes. I will make you the host. Okay.
Okay.
Yeah.
Okay.
So now
he will not give you back, yeah? Great job, Luis. Great job today.
Yeah, we were
very
in
good,
time.
yeah.
Yeah, we were in time, and people was well behaved.
Yeah, fantastic. Congratulations.
There is a very beautiful bottle behind you, Cesar. Yeah.
No.
Oh, good. Yeah.
Yes. Yes, that's true, yeah.
Are
Yes.
you speak? Can you hear us?
Yes. You can see, yeah? Yeah.
I guess Fia is not there any longer.
I brought from Cusco.
Very nice.
You see, yeah?
Yes.
I have more one there, you can see. Yeah? Yes?
Yeah.
Can you see?
Yes, they are good.
Yes.
But I was interested in the bottle behind you, in the bottle. Jack Daniels.
Okay. This is not the apartment where I live. This is a small apartment I rent
I see.
close by to my apartment because my wife doesn't like too much. I have such things. Yeah.
Okay, good.
And so
you see how I'm suffering with this nice view in front of me.
Stoker was looking for that yesterday. Tried to figure out what kind of battles I have. Yeah. But after I was sick and then recovered, I don't drink anymore. At least I don't know for long, but how long?
Okay.
So this is for my guests. So when you come to Brazil to visit me, for my guests.
Okay. Thank you. Yeah, I will have it in mind.
Yeah.
All right.
It's it looks a good. That is a very good attraction for invitation. Yeah.
Excellent.
Step away for just a moment. I'll be right back.
Yes, of
All
course.
right.
Okay.
You don't mind?
Excellent. So, well, I need to leave, Cesar. So
No,
see you
that's okay.
tomorrow.
That's okay. A great day, and you was
Yeah,
really
very good. Very good.
very
Yeah.
great today.
Yeah, and the speakers
Excellent.
were just fantastic. Yeah.
No, and gave us confidence because we have this problem with internet. An accident close by
Yes.
my
Yes.
yeah, and so what to do? Yeah?
Yeah,
Things like
but
that happen.
as
Okay,
Jorge.
Luis.
Yeah.
Luis,
Excellent.
please remember next year. We are thinking about the possibility to organize an hybrid kind of meeting, type of meeting, hybrid,
Right.
yeah,
Yes. That would be fine. Yes.
presential and also virtual. So we
Yes.
have to organize these things more carefully than this time, because okay, we are in a hurry. We could do so much. We did the best we could, but we can organize, yeah, and a
Yes, that's true.
hybrid.
That's true. This
Yes,
asynchronous talks would be very good to have it
yeah.
next year too. Yeah.
So we are counting on you, yeah.
Yes, of course. I will be here, and I want to go to Teotihuacan again. Yeah. I will be there.
Yes,
Yeah.
that's fantastic. So we are counting on you. Very good.
Yes, of course, Cesar. Excellent. So, well, see you tomorrow. Have a
Yes.
nice afternoon.
See you tomorrow, yes.
See
Yeah.
you tomorrow, Luis.
Yeah.
Tomorrow.
Bye bye.
Nos vemos mañana.
Mañana.
Bye.
Sí, mañana.
Mañana. Excelente.
Sí, por supuesto. Claro. Muy bien. Muy bien hecho.
I'm anxious to go to Teotihuacan too.
Yes. I am also anxious to do that. You know, I am really anxious. It's
The original idea was good because after I described the astronomy there, then if we would, a couple days later, everyone went out on the excursion, they would have had something to really look for.
Yes. That's really great. We have to think also about these talks. About the talks directly involved with this environment, local environment, and the mayors and so on. So you have to think about, Stephen,
Yes.
who should we invite for the next time to have,
I
we have
will.
the, yeah.
I will think about that because I do
Yeah.
know of people that we could ask.
Yeah, that would be fantastic because we can, have a very interesting possibility to know much better about this historian, ancient, cultural, Mayan history. Yeah? So that will be great to have also someone to give. Just 1 second. Oh. Oi, Helena. Eu te ligo daqui a um pouquinho, só um minutinho, tá? Eu tô no ar aqui. Okay. So I have to see what to do.
I wanted to say, just now after we've had 5 days of the conference and the virtual presentation here, the format that we arrived at that different people contributed to, I think is just working fantastically, just like we're hearing from the audience, to have the combination of the plenary talks that are live, and then the concurrent talks. There's so many of them that has to be 5 minutes, but that is working because the talks are video recorded and available for people to see. And then the extra dimension of the posters, because, you know, like you were saying the other day, and a regular poster session, the posters are just hanging and people look at them in breaks, and that's about it. Here, we've got the video recorded about the posters, and the poster presenters get 3 minutes to talk about. So everybody is getting a much better idea of what's in the posters than they might otherwise. So it's working really well.
Yeah, that's true. They can have visit the posters many times. Yeah, and also the videos. I saw the videos many times because, of course, we and Ben were implementing, you know, the insertion of all these videos in the YouTube. But we have to look, we have to analyze, we have to work on it. And it was really great because it was fascinating. It was very rich conference. If because maybe do not believe it, but I was involved in more than 40 international conferences in my life. And this certainly is the conference I learned most than the others because it was really great.
It is great. We've got people literally all over the world. And,
yes.
And it just goes to show what we already know, that there are brilliant people everywhere, and they're coming and sharing their work with everyone else here.
Yeah, and we should be open-minded for that. And so I think to organize a hybrid meeting will be a challenge, yes. But I think if we divide our group in 2 teams, yeah, me and Beno with the virtual team, and the others with the presential one. Of course, the virtual team with the participation of Mariana also for the poster sessions. If she take care, Mariana and Luis, yeah, and Gabriela, with respect to the poster virtual section, yeah. And the other parts of the virtual, I mean, the other type of meetings, of categories, virtual categories, Ben and I, we can share and organize. And Peter, with the presential part.
I have some friends and colleagues who did a hybrid conference not too long ago, so I'll ask them if they got any advice, any thoughts to share on what they found was the best way to do both at the same time.
Yes. I think that would be great to have some advice on this topic, because also will be our first meeting, a hybrid meeting we organize in our lives. And so
I would like to think it'll go well, because this is our first virtual, and it's
that's true.
But Stephen, we also like to thank you that we have access to this stable platform at your university, which is a great help. It is stable and it is robust, so we can count on that.
It's really
it's very important.
Very stable.
Many thanks to you and to the technical team.
If we went into a private account of some sort, who knows whether it would have been stable or not, like this one is. And then
yes,
of course, having technical support through Jeremy from the university was very good.
And do you think, Steve, we can have also from your university the possibility to organize the virtual part in 2021 again with Jeremy and the others? I mean, the technicians and the.
I definitely think so. Yes.
Yes.
I will keep pursuing it, but I don't see any reason why not. The way that their system works right now is for the larger webinar. Jeremy said it's first come, first serve. So as long as I get my request in real early, then we shouldn't have a problem.
Yes. Yeah, that would be great, because that would be really great.
Many thanks to you and to Jeremy, please.
That's okay. Okay, Stephen, I think we can rest a bit. I will try to finish the program for tomorrow, okay? And then
Yes.
I send to you, okay? I'm
like-
late today, but today
That's
you know,
okay. I need to take a break for a little bit before I sit down and program everyone's names for tomorrow anyway.
yeah. Okay.
This
See
technical
you.
problem at the beginning took some
See
energy of
you.
us, yes. See you all together. See you tomorrow.
See you tomorrow.
Yeah. Thanks for the great job. Yes.
Thank you. Thank you.
Well, thank you.